Hi there, you're in the lab with your mate JJ. Today is Old Book Teardown. Today we're going to do an Old Book Teardown. Of course, in the Old Book Teardowns, we take a look at an old book and see what's inside of it. My silly job title for today is Technical Director. Today I'm the Technical Director, and the book that we'll be looking at is Principles of Electronic Circuits, 2nd edition, by Stanley G. Burns and Paul R. Bond. This book is one of the books being referenced by the Learning the Art of Electronics coursework, which we're in the process of beginning. So we're going to just tear through this today. We're going to have a look at what's inside. It will be a fairly long video. I don't know exactly how long yet, but we'll find out. The book was published in 1997. So it meets the criteria for old books. Old books are anything published before the year 2000. So this qualifies. So what we're going to do is we're going to pop over to the bench and we're going to flip through this thing. We'll have a look at the back, we'll have a look at the front, we'll go through the table of contents, and then we'll flip through and just have a bit of a squiz at what's in the book. We won't be looking at anything particularly close detail. We'll just be flipping through. So let's jump over to the bench and get on with it. Here on the bench, this is our book. It includes CD-ROM, but of course we didn't get the CD-ROM. But my friend from the Learning as a Hobby channel, he has it, so he's going to send it to me. So I'm looking forward to having that. I'll try to remember to update the show notes for this video with the CD-ROM when I get my hands on it. It hasn't arrived yet, but I'll update you about that. So yes, this is, as I said, the 2nd edition of this book, published in 1997. The CD-ROM has evaluation version of P-Spice plus Spice Netlist, electronic workbench circuit models, and Acrobat transparencies. I think that just basically means PDF files that you can scan. On the back, okay. Okay, join us on the internet via the World Wide Web, Gopher, FTP, or email. So we have Thomson website. They've probably still got that. Gopher at gopher.thomson.com. That's probably not there anymore. FTP at thomson.com. Wow. And email, find it at kiosk.thomson.com. Wow. Thomson.com is the online portal for the products, services, and resources available from International Thomson Publishing, ITP. This internet kiosk gives users immediate access to more than 33 ITP publishers and over 20,000 information resources. Through Thomson.com, internet users can search catalogs, examine subject-specific resource centers, and subscribe to electronic lists. You can purchase ITP products from your local bookseller or directly through Thomson.com. For information on our products and services, please email to info@pws.com or point your web browser to www.pws.com, a service of ITP. There you go. So isn't that interesting? So of the 4 technologies, email, still going gangbusters, World Wide Web, still going gangbusters, but of course now it's all HTTPS, not HTTP. Gopher, totally obsolete. FTP, totally obsolete. I mean, they're still out there, of course, but not much. So let's have a look. Principles of Electronic Circuits, 2nd edition, Stanley G. Burns and Paul R. Bond, both of Iowa State University, Iowa. Okay. This text, thoroughly revised in its 2nd edition, provides students with a solid foundation in electronic circuits. The book features a useful class-tested program of study aids to guide students' learning and practical hands-on integration of SPICE throughout the book to motivate circuit analysis and design. Taking a fresh look at the skills and knowledge required of modern electrical engineers, the authors describe device models for diodes, bipolar junction transistors, and field effect transistors, and apply these device models in a wide variety of realistic examples. The authors then teach readers how to write netlists that apply SPICE to the development and justification of circuit models and compare their SPICE designs against analytically derived solutions. The book features superior new pedagogy with important concepts listed at the beginning of each chapter, marginal notes emphasizing key concepts in the text, more than 200 new example problems and circuit designs, new drill exercises and check-up questions at the end of each section and chapter, and actual device data sheets supporting the more than 1,000 end-of-chapter problems. Special features of the second edition. A bound-in CD-ROM contains the latest Windows evaluation version of PSpice, electronic copies of all SPICE netlists printed in the text, 150 Acrobat-based electronic transparencies of text illustrations, and sample electronics workbench circuit models derived from selected Burn/Bond SPICE netlists for use with the student edition of Electronics Workbench, available from PWS, making this book a complete course and design solution for instructors and students using PSpice and other circuit analysis tools. New optional reference chapter 18 on semiconductor fabrication, new coverage of exciting topics such as GAAS MESFET and microwave and photonic diodes, new appendices including an overview of SPICE netlist syntax, new 4-part text organization supporting a variety of 1- and 2-term course applications. And again, this is the PWS Publishing Company, Boston, Massachusetts. All right. And we're ready to go in. Now, it's got these really great cheat sheets in here. They're in the front. Are they in the back as well? I'm not sure. They've got a form in the back that you can write in to request or order something. We'll take a look at that at the end. But yeah, before we begin, this is really great. The tables of information they've got here. So we've got a table of physical constants. We've got Boltzmann's constant, elementary charge, electron rest mass, electron volt, permittivity of free space, Planck's constant, speed of light in a vacuum, and the thermal voltage at 300 Kelvin. And we've got conversion factors and prefixes. For units, we've got angstrom unit, angular frequency, micron or micrometer, mil. Yeah, mil. A mil is 1,000th of an inch. But of course, all of the Americans knew that already. Temperature, Celsius. And then there's the femto, pico, nano, micro, milli, kilo, mega, giga, tera. Fair enough. Table 2.2, useful properties of crystalline silicon, germanium, and gallium arsenide. Wow, okay. These are, of course, the semiconductor materials that you can use to make semiconductors. What have we got here? Oh, I see. So this just follows on. Oh no, okay, this is figure 218. Properties of doped silicon. There you go. And it's a log scale along the x-axis. Oh, here it's a log scale on both axes. Okay. And then we've got more tables. We've got typical bipolar junction transistor parameters at 300 degrees Kelvin, which is room temperature, about 25 degrees Celsius. Okay. 2-port feedback summary. Okay. And then we go on. We've got a couple more. We've got selected diode model parameters. This is for your SPICE net lists. Selected SPICE BJT model parameters. Selected SPICE MOSFET model parameters. Okay, so this book is big on SPICE. It's a topic I don't know particularly well yet, but I do intend to learn more about it. Of course, it's LT SPICE that I have these days. I don't have P SPICE, if it's even still around. Who knows? That's 27 years ago. A lot would have changed since then. So again, we've got a little title page here. Burns and Bond, both from Iowa State University. Publishers are based everywhere. Not in Sydney though. All right. And on we go. Here's the table of contents. So we've got a preface, and we've got preface for students. We've got part 1, semiconductor devices and basic circuits. Chapter 1, electronic circuit fundamentals. Historical perspective, electronic signals, amplification, ideal operational amplifier. Chapter 2, introduction to semiconductors. Charged particles in a solid, drift and mobility, conductivity, diffusion, energy band theory of solids and overview, semiconductor materials, properties of intrinsic silicon, properties of doped silicon, experimental studies of drift and diffusion. Chapter 3, Semiconductor Diodes and Diode Circuits, the p-n junction in equilibrium, the externally biased junction, the diode equation, practical diode characteristics, load lines and piecewise linear diode models, dynamic resistance, rectifier circuits, breakdown diode voltage regulator, diode wave shaping circuits, diode logic circuits, diode analog switch, diode capacitance and switching times, metal semiconductor junctions, photonic and microwave diodes, diode heating, SPICE model for the diode. Chapter 4, the bipolar junction transistor, basic BJT operation, volt-ampere equations for the BJT, BJT regions of operation, the common base configuration, the common emitter configuration, cutoff in the CE configuration, saturation in the CE configuration, inverse mode, CE current gain considerations, maximum ratings for the BJT, switching times for the BJT, SPICE models for the BJT. Chapter 5, the field effect transistor, notation and symbols, MOSFET operation, MOSFET specifications, metal oxide circuits, SPICE model for the MOSFET, JFET operation, JFET specifications, field effect transistor small signal models, JFET circuits, SPICE model for the JFET, MESFET operation. Part 2, linear circuits. Chapter 6, basic analysis techniques, operational amplifier specifications, general feedback concepts, Bode magnitude and phase plots standard forms. Chapter 7, biasing and stability, BJT Q-point selection, BJT Q-point stabilization, FET bias and stabilization, BJT current sources, MOSFET current sources. Chapter 8, small signal mid-frequency amplifier analysis, the hybrid pi model, the common emitter amplifier, impedances and amplification, the common base amplifier, impedances and amplification, the emitter follower amplifier, impedances and amplification, the FET model, MOSFET amplifiers with active loads, discrete cascaded amplifier stages, direct coupled and bi-CMOS amplifiers, instrument of BJT hybrid parameters. Chapter 9, frequency effects in small signal amplifiers, high frequency small signal BJT and FET models, the effect of CMU and CGD, the Miller effect, Small signal amplifier low frequency analysis, direct coupled and bi-CMOS amplifier examples. Chapter 10, operational amplifier circuitry. Differential BJT amplifiers with resistive loading, differential MOS amplifiers with resistive loading, differential JFET amplifiers with restrictive loading, BJT amplifiers with active loading, MOS amplifiers with active loading, power output stages, effects of device mismatch. Chapter 11, feedback. Overview of general feedback concepts, voltage shunt feedback, current series feedback, voltage series feedback, current shunt feedback, amplifier frequency dependence and compensation, oscillators. Chapter 12, operational amplifier examples. Design of an operational amplifier using a CA3096 NPN/PNP transistor array. Analysis of a MU-A, that's a microamp, I guess, 741 operational amplifier. Analysis of a CA3140 operational amplifier. The LM111 comparator. Trends in operational amplifier performance. Part 3, Digital Circuits. Chapter 13, Integrated Circuit Logic Gates. Digital operation of circuits. Basic gate terminology. Early integrated circuit logic families. Transistor-transistor logic, emitter-coupled logic, NMOS logic, complementary MOS logic, integrated injection logic, comparison of logic families. Chapter 14, Small Digital Subsystems, Combinational Logic Circuits, Sequential Logic Circuits, Monostable and Astable Timing Circuits, Data Systems Examples. Chapter 15, Semiconductor Memories, Overview of Semiconductor Memories, Introduction to Memory Organization, Read-Only Memories, Static Read-Write Random Access Memories, Dynamic Random Access Memory, Charge-Coupled Devices, Gate Arrays and Programmable Logic. Chapter 16, Analog to Digital and Digital to Analog Conversion, Analog to Digital Conversion Process, Digital to Analog Conversion, Analog to Digital Conversion. Chapter 17, Additional Examples of Analog Integrated Circuits, Analog Systems Overview, Series Pass Voltage Regulator, Switching Regulators, Analog Multipliers, Phase Lock Loop, System and Circuit Description, Phase Lock Loop Applications. Part 4, Semiconductor Technology. Chapter 18, Basic Fabrication Technology and Device Constraints, Impurity Diffusion, Ion Implantation, Resistive Properties of Doped Layers, Photolithography and Masking, Resistors, Capacitors, NPN transistors, PNP transistors, diodes, junction field effect transistors, metal oxide semiconductor transistors. Appendix A, List of Symbols. Appendix B, Physical Constants and Conversion Factors. Appendix C, Number Systems and Boolean Algebra. Number Systems, Basic Functions of Binary Variables. Appendix D, Introduction to SPICE. Basic Circuit Models for SPICE. Element Statements, Sources, Active Device Models for SPICE. Appendix E, Two-Port Model Summary. Appendix F, Answers to Selected Problems. And the index begins on page 967, making this book about 1,000 pages. About 1,000 pages. Now we will read the preface together, but first I'm going to go make coffee. I'll be right back with the coffee, of course. All right, I'm back with my coffee. We're going to go through the preface together, and it's a fairly long preface. Okay, and then there seems to be showing the course, and this is the preface for students. Okay. Well, I guess we're going to go through the preface, and then we'll be away on the rest of the book, which we'll just flip through. So let's see what they had to say in the preface. Principles of Electronic Circuits, second edition, is an introductory text for upper-level sophomores and juniors in electrical or computer engineering. There have been significant changes in organisation and content between the first and second editions to reflect recent technological and pedagogical trends and the need to provide the fundamental knowledge in electronic circuits for students practicing their discipline in the 21st century. New to this edition, the first edition of this book has been used at over 40 engineering schools. The manuscript leading to this second edition has been class tested by hundreds of students and their professors. There are numerous changes in the second edition, representing an over 80% revision from the first edition, both in content and pedagogy. Organisation. The second edition has been divided into 4 sections, consisting of a total of 18 chapters to make it easy to tailor the text to a wide variety of course sequences prevalent in electrical engineering and computer engineering curricula. Over 1,000 analysis and design problems. Selected problem answers are given in Appendix F. Integration of SPICE. Of special note is the integration of SPICE throughout the text and the expanded emphasis on metal oxide transistor circuit analysis and design. The use of SPICE includes the development and justification of SPICE models, as well as their incorporation into a number of annotated analysis and design examples. The SPICE solutions are compared to analytically derived solutions. The CD and other ancillaries. The second edition includes a package of electronic tools provided on the CD-ROM bound into the back of this book. The CD-ROM contains the evaluation version of PSpice from MicroSim for Windows-based computers. There's a note here. Windows is a registered trademark of Microsoft. This is just trademark stuff. Who cares? Okay, electronic copies of all the SPICE net lists printed in this book, plus some additional ones that demonstrate important concepts. Sample electronics workbench circuit models derived from selected Burns-Bond SPICE files for use with the student edition of Electronics Workbench available from PWS. A slideshow, QuickTime video for Windows movies, and demonstration version of the Electronics Workbench software for Windows. Acrobat transparencies of selected Burns-Bond text illustrations provided with the Acrobat Reader for Macintosh and Windows computers, which can be used by instructors to display text illustration during lectures or as a study aid by students working with computers at home. In addition, the following ancillaries are available with this book. The Instructor's Solutions Manual, which has work solutions to every problem in the book. The second edition lab manual contains labs written by the authors covering a wide spectrum of key topics studied in the course. BJT and MOS circuit design. The student is guided in designing basic BJT and MOS circuits into a variety of digital and analog integrated circuits. There are detailed discussions of widely used diode circuits, BJT and MOS amplifier circuits, current sources and mirrors, multi-stage amplifiers, including the operational amplifier, oscillators, logic families, MSI circuits, memories, analog to digital and digital to analog converters, voltage regulators, multipliers, phase detectors, and phase-locked loops. CMOS and bi-CMOS circuits. There is significant increased emphasis on CMOS and bi-CMOS circuits. Coverage of semiconductor fabrication. Because electronic circuit performance and concomitant limitations ultimately depend on the device technology employed, we have included a chapter on semiconductor fabrication that could be used in a course sequence or as a standalone reference. Other contemporary topics. Other topics of contemporary interest, such as the GAAS MESFET and microwave and photonic diodes, are included in this edition. Pedagogy. 2 colors have been used effectively to clarify diagrams, of which there are over 900, and guide students in their study of the topic. Margin notes are included throughout the text to provide clarification and expansion of key points. In addition to a wide assortment of problems, we have expanded our use of the examples with solutions and added drill exercise and checkup questions in each section. More challenging end-of-chapter problems are marked. Actual device data sheets are used to support the technical material and chapter problems. To assist the student, each chapter starts with a list of important concepts and concludes with a list of survey questions. Students are also encouraged to read Preface for Students, which contains valuable hints on using our pedagogical tools. The appendices, which include an updated list of symbols, physical constants, and conversion factors useful throughout the text, number systems and Boolean algebra, an overview of SPICE netlist syntax, a two-port model summary, and answers to selected problems, are designed to support the student's study of electronic circuits. Features. Contemporary electronic circuit analysis and design uses CAD tools, especially SPICE. SPICE-based solutions are integrated throughout the text, and SPICE models are presented for the diode in Chapter 3, the BJT in Chapter 4, and the FET in Chapter 5. SPICE solutions and the approximate calculator-based algebraic solutions, which offer insights into electronic circuit behavior, are compared. Virtually all versions of SPICE programs use the same models and syntax, although there are differences, especially in output format and user friendliness. The SPICE listings presented in this text are based on PSpice without schematic capture. The authors believe it is important for the student to be able to write a netlist for a circuit, even though schematic capture is often mechanically easier to use. Appendix D provides a summary of SPICE syntax and formalisms used to write netlists. In keeping with the general use of mixed CGS, MKS, and English units in the technical and trade literature, we will use these mixed unit conventions, explaining variations as necessary. Key conversions are provided in Appendix B. A large selection of problems is included at the end of each chapter, over 1,000 in total. There is a variety of both analysis and design problems, some using SPICE. References and selected reading are provided at the end of each chapter. A list of symbols is given in Appendix A. Inclusion of selected manufacturer's data sheet throughout the text make it easier for the teacher to assign design problems. Overview and organization. The emphasis and organization of the second edition are tailored to serve a variety of curricula. The text is organized into 4 sections. Part 1, Semiconductor Devices and Basic Circuits, consists of chapters 1 through 5. Part 2, Linear Circuits, consists of chapters 6 through 12. Part 3, Digital Circuits, consists of chapters 13 through 17. And Part 4 includes a single chapter, Chapter 18, Semiconductor Device Fabrication. Figures P1 through P4, which we will discuss shortly, illustrate the organization of these chapters into various course sequences as found in most schools. The text assumes that sophomore engineering and physics students have an elementary calculus and physics background, as well as expertise in the solution of AC and DC circuits by means of Kirchhoff's laws. Several of these key circuit concepts are reviewed in Chapter 1, Electronic Circuit Fundamentals, which is included to serve as a review of basic circuit analysis techniques, as well as an overview of the operational amplifier as a system building block. A cursory overview of semiconductor device physics is provided in Chapter 2 to give students insight into the validity of device models that are used throughout the text. Chapter 2 may be used as a reference resource in those curricula having a more formal solid-state physics course. It is assumed that the student has access to and a working knowledge of computers because SPICE is used throughout the text to support electronic circuit analysis and design. Most curricula include a separate course in digital systems where number systems, Boolean algebra, sequential logic theory, and logic reduction are studied. For this reason, and because this material is not essential to our purpose, we have elected not to include a chapter on these topics. Chapters 13 through 15 in Part 3 do summarize key terms as needed for those students with no previous exposure to these topics. Number systems and Boolean algebra are summarized in Appendix C. The microprocessor has become the central feature in virtually all electronic systems. Indeed, virtually all electronic systems are smart. That is, they include microprocessors and associated logic and memory circuits. We have chosen not to treat microprocessor internal architectures or features in depth, preferring to consider these topics worthy of a separate course. However, we do discuss the microprocessor in system design and in interfacing to system buses in chapters 15 and 16. Possible course topic sequences. So these are different ways that you could use this material in a course. There's this one is the 2-semester sequence, and then there's a 1-semester course. There's a 3-quarter course, and then there's courses with digital emphasis. Okay, so if you're interested in that, well, you have to get yourself a copy of the book and have a close look at it. They finish up here. We believe that all electronics courses should include a strong laboratory component that merges a student's analytical knowledge base, computer modeling and simulation tools, and hands-on laboratory design and measurement experiments. And then they've got a bunch of acknowledgements, and then we're up to the preface for students. Now, I have read this before, and it's kind of interesting. They talk about the SQ3R method, which we'll read about it. We'll read this. All right. So this is the preface for students. The objective of this book is to introduce the electrical and computer engineering student to the broad range of electronic circuits, both discrete and integrated, and both analog and digital. Our intent is to develop your ability to analyze and design a variety of electronic circuits systematically through examples ranging from the simple to the complex of classic and contemporary practice. Our procedure will be to present just enough physical concepts to give an insight into the behavior of the semiconductor junction. We will then proceed to propose models for semiconductor devices such as diodes, bipolar transistors, and field effect transistors. The major emphasis will be in studying the behavior of the device models in the context of practical circuits. Inherent in this approach is an awareness of the accuracy and range of validity of the models that are being used for the various devices. The text is divided into 4 parts as follows. Part 1, semiconductor devices. Part 2, linear circuits. Part 3, digital circuits. And Part 4, semiconductor technology. After Part 1, the parts may be read in any order. You need to have taken an introductory linear circuit analysis course and mastered Kirchhoff's current and voltage laws, and to have a mathematics background through simple integration. You should also be familiar with a computer circuit simulation program such as SPICE. For Part 3, it is helpful if you have had some exposure to logic systems and the binary number system. We hope to help you develop your skills as a problem solver. Educational researchers have learned that problem-solving skills are not necessarily learned simply by routinely solving more and more problems. The use of proven problem-solving strategies and techniques greatly accelerates the development of these skills, and later in this preface we discuss sound approaches to learning technical material and to problem solving. You will find that we prefer to make simplifying assumptions and quick approximate calculations when that approach is justified. This develops a feel for what is going on in the circuit. You will also see when the more accurate computer simulation is better. Computer simulation of electronic circuits with SPICE is used as a powerful analysis tool in a number of examples. While programs that perform the simulation after schematic capture are readily available, we find that much more attention to detail takes place when students first practice developing a netlist. Our examples show typical netlists and model statements. You will want to use some of the resources provided on the CD-ROM included with this text. See pages 10 to 11 for a description of the CD-ROM contents. I think we saw that already. Structure your studying and your learning. You might think that your engineering studies are difficult. Well, they are. However, some of this difficulty may be due to improper or ineffective study methods. To develop good study habits, you may need to add structure and discipline to your studying. You may benefit from use of formal study techniques, which can greatly increase your learning efficiency. Techniques that you can try to improve your studying and learning that we address include reading, note-taking, problem-solving, and assessment of your learning. However, in the end, you must decide what works for you. If you solve the problem of developing strong study methods, you have taken the first step on the way to becoming an engineer, a problem solver. The methods we outline below are not all our own. In the following discussion, we acknowledge the contributions made by various authors and educators as we adapt their work for this book. Additional insight to effective teaching and learning can be found in the book by Stice. There's notes down here. So we've got a reference to developing critical thinking and problem-solving abilities. Okay, by J.E. Stice, published 1987. Okay. Reading, the SQ3R method. The process of reading a textbook for understanding is not the same as that of reading a novel for entertainment. One does not ordinarily skim over a novel to get the high points, jump to the end to find out how it ends, and then go back to fill in the gaps. This approach would defeat the objective of reading a novel. However, that is just what you should do when studying a textbook to maximize your potential for understanding and retention. A formal procedure that has proven to be very effective in improving textbook reading comprehension and grades is the SQ3R method developed by Francis Robinson. There's a note down here, Effective Behavior, published 1941. Wow. The symbols SQRRR stand for survey, question, read, recite, and review. The 5 steps are discussed below. Survey. Skim over the assignment before you begin to read for details. At this point, read only the article headings, figure captions, and the chapter summary. Also look for the highlighted material and other points of emphasis that indicate key ideas. You should get a global perspective of the assignment so that you know your objective before you start to read. Question. Break the assignment into manageable pieces by formulating questions that you will want to ask and answer about each article. Use the article heading, figure captions, etc. as guides to ask yourself questions about the material. Be as specific as possible. Jot down your questions in outline form and leave room for answers that will follow. This step is intended to create a structure for storing or remembering the detailed information that you will learn when you read. This book is printed with liberal margins to give you space to take notes and write questions. Use this space to your advantage. Read. Now you have prepared yourself to absorb the new information. Next, read for details. Read a small amount of material at a time. If the material is difficult or confusing after the first reading, don't go on. Instead, go back and reread the article, maybe just a paragraph or 2 at a time. Recite. After you have read a section, stop and recite what you have read. Try to answer your questions. Take notes on your outline. If your initial set of questions is incomplete, ask and answer more questions. Don't go on to the next section before you have summarized the main ideas in your own words. Repeat the question. Read and recite. Repeat the question, read, and recite cycle for each section until you have completed the assignment. Review. After you have read the entire assignment, skim over the assignment again, review your notes, and ask and answer your questions again. Try to apply the material in ways that are not discussed in the text. If possible, work with a companion and quiz each other on the material. In electronics circuits courses, it will usually take several class periods to cover the material on a particular subject or chapter, so the topic does not have to be completed in a single study session. In fact, it is probably best that you use several shorter study sessions to complete your reading of a single chapter or section. This will give you a chance to think about the material and review it more frequently. We have organized this text to facilitate use of the SQ3R method. At the beginning of each chapter, introductory remarks provide an overview and a general perspective on the chapter. A list of important concepts is presented, and sample survey questions are posed to guide your reading. However, you are encouraged to perform your own survey and develop your own set of questions as well. The book is liberally illustrated with sketches, circuit diagrams, graphs, and tables that are tightly integrated with the text. Equations and figures are systematically numbered so that once developed, they can be referenced easily from anywhere in the text. Checkups are inserted at the end of various sections to remind you to recite. This is an opportunity to answer your questions and a few short questions that we have prepared. This is also a chance to complete your outline. Also, new terms are italicized and definitions as well as key concepts are flagged by notes in the margin. At the end of each chapter, highlights of the chapter are provided for your survey and review exercises. Note-taking. Your task in taking notes in a lecture is by far different from that of a court stenographer. The stenographer is obliged to record every word that is spoken. Your objective is to capture the main ideas from the lecture with sufficient accuracy and organization that you can use your notes later as a study aid. Some simple hints for effective note-taking are: come to class prepared. Do the assigned reading before class and bring your SQ3R notes. Ask your questions when the instructor is discussing the topic that confuses you. Jot down his or her answer on your outline. Imagine that you are taking notes for your best friend who could not make it to class. Your objective is to give your friend an organized set of notes that record the key points of the lecture. Your lecture notes can be a supplement to your SQ3R notes. Listen for key words that signal main ideas. The three primary reasons that, an alternative explanation, in other words, a conclusion or summary statement, finally we can say that, or a change of direction, on the other hand. Do not assume that the instructor will write everything that you are expected to know on the board. Read everything that is written and listen to everything that is said, but be selective in what you write down. After class, but before the next class, rewrite your SQ3R notes and your lecture notes into a single organized unit. This is another opportunity to review the material and solidify your understanding. Develop problem-solving skills. Before we discuss how to become a better problem solver, perhaps we should decide what we mean by problem solving. The following definition was proposed by D.R. Woods. There's a note here. Teaching problem-solving skills, published 1975. Okay, the following definition was proposed by D.R. Woods and is appropriate for our use. Problem solving is the process of obtaining a satisfactory solution to a novel problem, or at least a problem that the problem solver has not seen before. This definition means that problem solving is more than just working homework problems by following examples in the book. Real problem solving requires that we use our knowledge and understanding of facts and principles, our ability to apply those facts and principles, and our perceptiveness to comprehend the new situation. With all this, we can solve novel problems, problems for which we do not see an immediate solution. An important element of problem solving is an organized strategy to follow. We outline the strategy developed by Polya. Okay, Polya here, How to Solve It, second edition, 1971. Okay, developed by Polya and modified by Woods in 3. It's the same reference to the one from earlier. Initially, it is important to pay close attention to each of the steps. Then, as you become more experienced and successful, you will be able to develop your own personal variation on the strategy. For now, try the following steps when you solve a problem. Define. Define the actual problem. Often, unnecessary, incorrect, or misleading information is given or collected that might distract you from the real problem. Think about it. Don't jump into your solution without getting acquainted with the problem. Identify the attributes of the problem. Summarize and organize what is given. Draw sketches. What area of knowledge is involved? Do you have enough information to solve the problem? Have you solved similar problems before? Plan. Flowchart a solution. Where do you start? What sequences of steps will lead you to your solution? Can the problem be broken down into manageable pieces that can be solved one at a time? Think about alternative plans in case you get stuck. Carry out plan. Follow your plan to solve the problem. Look back. Did you solve the problem that was posed, or did you solve some other problem? Is your solution reasonable? Did you make any mathematical errors? Check for correct signs, decimal point location, transposed digits, etc. Did you present your solution and your answer in a fashion that is logical and readable? Throughout the book, we include step-by-step procedures for problem solving in a large number of examples. Assessment techniques. Assessment is the process by which we find out what we are learning and how well we are learning it. When we think of assessment, we usually think of exams. However, there are several other assessment techniques that we can and should use continually to monitor our learning. We have adapted a selection of assessment techniques from Angelo. Okay, that's number 5. Classroom Assessment Techniques, a handbook for college teachers, published 1993. As components of homework problems. The techniques are outlined below. Keep in mind that using the assessment technique itself contributes to enhanced learning. Documented problem solutions. When you solve a problem, it is not sufficient to get the right answer. You must also understand how you solve the problem and how the approach can be adapted to other situations. Documented problem solutions can help you achieve this understanding. The technique involves adding to your solution a detailed written explanation of the process that you use to obtain your answer. It is important that you clearly explain each step that you take and why you make certain decisions. Of course, it is valuable to refer to example problems when you are solving your homework problems. However, it is not good simply to compare your problem statement to an example and then blindly follow the procedure used in the example. Directed paraphrasing. One of the most difficult tasks that an engineer faces is communicating highly technical and specialized information in everyday language that can be understood by non-technical people, including clients, customers, friends, parents, etc. Directed paraphrasing is a technique in which you use your own words to paraphrase a concept for a specific audience with a specific need to know. Directed paraphrasing will help you to develop your communication skills. In addition, the exercise of composing, in your own words, an explanation of a concept will help you gain a more complete understanding of the concept. Student-generated test questions. The process of solving the homework problems at the end of each chapter is basically a passive response. That is, you answer questions that are posed, but generally, you do not expand your solution beyond what is required of you. Ideally, your studying should include more active involvement in developing both questions and answers. The process of generating your own test questions is a valuable technique that allows you to organize the many facts that you have gathered and synthesize them into something of your own creation. Then you can proceed to solve your exam questions as a drill on the topic material. It is also an opportunity for you to discover what aspects of the topic material you do not understand. As you develop your own test questions, you are actually beginning to prepare for the upcoming test. You may identify what concepts are most important, how knowledge of these concepts can be demonstrated through the test question, and what constitutes a complete solution to the question. Generating good test questions is a difficult task. If you take these exercises seriously, you are more likely to develop greater understanding and improve your performance on real exams. Final words. An old saying goes, what I hear, I forget. What I see, I may remember. What I experience, I know for life. Students in engineering tend to be visual sensory learners. For this reason, this book is heavily illustrated with circuit diagrams, transfer characteristics, timing waveforms, and computer-generated plots to help you visualize what is going on in electronic circuits. We encourage you to become personally involved with the subject so that you can experience the excitement of electronics. Apply what you learn to your own life and know it for life. We have done all we can to get you off on the right foot. The rest is up to you. Now start your study of electronic circuits with our best wishes for your success. All right. And on we go. So this is part 1, Semiconductor Devices and Basic Circuits. Part 1, consisting of chapters 1 through 5, provides you with a basic understanding of key semiconductor devices and their circuit applications. Chapter 1 is a review of basic circuit theory and concepts. Chapter 2 introduces the concept of drift and diffusion, as well as the basics of the physics of semiconductor devices. The material properties of resistivity, conductivity, mobility, and temperature dependence are introduced, along with typical values for electronically interesting materials. Although many of you may cover these topics in more details in physics courses or in another advanced semiconductor course, it is important that key concepts and terminology be introduced early to support the device models and specifications that are required for electronic circuit design and analysis. Although the focus is on the properties of doped and undoped silicon, there are references to 3 to 5 materials, metals, and insulators, especially SiO2, which is a technologically important material. You may elect to use Chapter 2 as a reference, especially if, as mentioned, the Chapter 2 material is covered elsewhere in your curriculum. In Chapter 3, p-n junction theory, including p-n junction characteristics and large and small signal diode models, is presented. This is followed by a selection of representative diode circuit applications, including power supply rectifier circuits and various signal conditioning and switching circuits you are likely to encounter as subsystems in integrated circuits. The SPICE model for the diode is presented along with examples of its use in designing power supply circuits. Bipolar junction transistor principles are presented in Chapter 4. Models are developed for cutoff, active, and saturation regions, and representative circuit configurations are discussed. Small signal models are also introduced. As in Chapter 3, the SPICE model is introduced and applied to some example circuits. Temperature effects, capacitances, and switching speed are studied here to provide an understanding of the limitations of device structures. Similarly, Chapter 5 takes up the operation, models, and circuit configurations for MOS and junction field effect transistors. Specifically, the basic operation of the MOS transistor is explained along with key IV characteristic equations. From these equations, we show the derived SPICE model and apply this model to some circuit examples. Although the focus is on MOS, we also explain the operation of the JFET and its high-frequency GAAS counterpart, the MESFET. The SPICE model for the JFET is introduced and applied to some examples. After this exposure to basic device operation, constraints, large and small signal models, SPICE models, and circuits, you are in a position to apply your background to a study of linear circuits in Part 2 or digital circuits in Part 3. So here we go. This is Electronic Circuit Fundamentals, Historical Perspective, Electronic Signals, Amplification, Ideal Operational Amplifier, Summary, Survey Questions, Problems. All right. I'm just going to take a quick break. All right, so these are the important concepts in this chapter. Fundamentals of circuit theory, including basic definition of signals, difference between AC and DC, and series and parallel circuits. Standard notation for representing a total, a DC, and an AC voltage or current. Double subscript notation. Linear superposition. phasor and phasor notation, difference between a digital and an analog signal, definition of the two binary states, 1, 0, high, low, on, off, ohmic and nonlinear IV characteristics, Thevenin and Norton source representation, equivalent circuits and source transformations, definitions of power gain and voltage gain, decibels and decibel, and phase calculations in cascaded linear networks, ideal operational amplifier, circuit diagram, terminal labels, characteristics and model, inverting amplifier topology and calculations, summing point constraints and application to ideal operational amplifiers, non-inverting amplifier topology and calculations, unity gain buffer, difference amplifier topology and calculations. Some photos here. This is the cat's whisker, I think they call it. The first transistor placed two closely spaced contacts, the emitter and the collector, on the surface of a germanium slab, the base. The V-shaped object is a plastic triangle around which gold foil was wrapped and at the apex and slit at the apex with a razor. It was held on the slab by spring pressure. Cool. So we're just going to start flipping through now. Oh, look at that. This is a flip-flop. Cool. The industry's first commercially available monolithic integrated circuit was this flip-flop from Fairchild Semiconductor, introduced in 1961. A member of the micrologic family, the chips used resistor-transistor logic, RTL, and held 4 bipolar transistors and 2 resistors. Reprinted by permission. Very good. Okay, they're saying this is the first integrated circuit. The first integrated circuit developed at Texas Instruments proved an entire circuit could be built with silicon. The bars, actually sections from a wafer of MESA transistors, became breadboard in this oscillator using silicon as resistors, capacitors, and transistors. Okay. Now this book is heavy on notation, and this particular this is like the Rosetta Stone. This little bit here, they tell you what the capitalization of the variables and the capitalization of the subscripts mean, and they indicate different things. I won't go through it in detail, but if you want to know, if you want to learn anything from this book, start with this section right here. That's very important. So yeah, they're talking about how there's a DC component and an AC component in voltage. Analog and digital signal definition, small signal discussion, Thevenin and Norton equivalent sources. So, okay. General one-port circuit, B, Thevenin equivalent circuit. So it's basically the Thevenin equivalent is a voltage source and a series resistor. And a Norton equivalent is a current source and a parallel resistor. Interesting. Amplification, the decibel. Decibels are basically a ratio, aren't they? I really don't understand it very well. It's got something to do, it's a log scale. There is nothing wrong with a ratio less than 1, although amplification usually implies a ratio greater than 1. Signal ratios can not only be very large, but also can be very small, depending upon the context and application. And look, I mean, you can just tell by looking, there's heaps of mathematics in this book. There's examples, drills, checkups. Okay. Ideal operational amplifier. This is, of course, the symbol. The person who had this book before me, they voltage gain AV, voltage input voltage VI, input resistance is RI, output resistance is RO. Isn't that interesting? All right. So they say that the inverting amplifier is a widely used electronic circuit. Okay, here we are at the summary. I suppose we might as well read the summary. In this chapter, we have introduced some of the concepts that will be required throughout the rest of this text. These include the basic circuit concepts of superposition, source transformation, and Kirchhoff's circuit laws. We recommend that if these concepts are unclear, you review them again before proceeding into later chapters, especially chapter 3 and beyond. The definition of an analog and digital signal was graphically presented. Notation conventions for DC, AC, and total voltage and current quantities, as well as cosine reference phases, were given. Voltage and current ratios are often stated using the decibel, and its use was illustrated for cascaded two-port networks. The ability to add phase shifts and gain in decibels arithmetically for cascaded two ports will be used extensively in part 2. Most importantly, from an applications viewpoint, the basic principles of the operational amplifier, along with conventions and a model and the use of the summing point constraints VI equals 0 and II equals 0 were introduced. Summing point constraints, as a consequence of employing negative feedback, were then used to derive the voltage gain for inverting and non-inverting amplifiers. Much more will be done with the operational amplifier in chapters 6 and 11. And we've got some survey questions and we've got some problems. And then we're up to chapter 2. This is chapter 2, Introduction to Semiconductors. Charged particles in a solid, drift and mobility, conductivity, diffusion, energy band theory of solids, an overview, semiconductor materials, properties of intrinsic silicon, properties of doped silicon, experimental studies of drift and diffusion, summary, survey questions, problems, references, and suggested readings. Our study of the principles of electronics will include selected topics in device physics, semiconductor materials, applications of semiconductor devices in circuits, and circuit design. This chapter treats some elements of solid-state physics that are helpful in understanding the fabrication and functioning of semiconductor devices. We will see, for example, what is meant when silicon wafers are specified as N or P type with a certain resistivity in ohm centimeters and a certain dopant. We will see what is meant by drift mobility, band gap, and lifetime, which are of interest in, for example, research on new compound semiconductors. It will become readily apparent that the field of electronics is a keystone in modern electrical engineering. In this introductory text, we intend to provide you with a basic foundation in semiconductor device operation and circuit design. These topics are supported by a brief qualitative treatment of solid-state physics necessary for an understanding of the functioning of devices and circuits. There we go. Important concepts in this chapter. Definitions of current, drift velocity, and mobility mu. Conductivity, sigma or NQ mu, and typical values. Resistivity, I think that's rho, equals 1 on sigma, and typical values. Typical values of resistivity and conductivity for good conductors, insulators, and semiconductors. Diffusion and diffusion current. Definition of VT equals KT on Q, and its value at 300 Kelvin approximately equals 26 millivolts. Fick's second law, diffusion equation, derivation, and solution interpretation. Energy quantization given by E equals HF equals HC on lambda, supported by calculations. Qualitative descriptions of the energy band structure for conductors, insulators, and semiconductors. definition and interpretation of conduction band and valence band energy levels and of the energy gap in a semiconductor, qualitative description of a hole, computation of the intrinsic electron concentration in a semiconductor, periodic table entries as related to elements used in semiconductor devices, properties of intrinsic silicon structure, energy band diagram, carrier concentration, conductivity or resistivity, and mobility. Definition of a dopant and the relation between doping concentration and carrier concentration, minority carrier suppression, energy band diagrams for N-doped and P-doped semiconductors, mobility and resistivity properties of doped silicon, typical N-type and P-type dopants in silicon, computation and resistivity and conductivity as a function of doping density, minority carrier lifetime and diffusion length and their experimental verification, method and results in the Haynes-Shockley experiment, charged particles in the solid, drift and mobility. Diffusion is an important concept as discussed in chapter 18. Okay. Mobility is a very important parameter for semiconductor materials. Okay. Conductivity is a very important, widely used semiconductor material parameter. Current density, not current, is used to quantify charge transport in a semiconductor. Equation 2.14 is a very useful equation. Okay. Resistivity is a very important, widely used semiconductor material parameter. Being able to list typical values and materials in these three categories is important. Okay, and here we go. So we've got a scale of conductivity. Oh, look at that. Quartz is hardly conductive at all. Ah. They're talking about wire gauge here. Okay. Diffusion. Okay, there's more in chapter 18. Energy band theory of solids and overview. This is one of those useful conversion factors worth remembering. One electron volt is 1.6 times 10 to the minus 19 joules. Wow. What was that? Energy levels for the hydrogen atom, quantized levels n through 6, or through n equals 6. 3 partial spectral line series are shown. Wow. I'm getting better. My understanding of atoms is improving. I still got a lot to go. Richard Feynman said, if you think you understand quantum physics, you don't understand quantum physics. So he also said, we don't expect you to understand, we just expect you to get used to it. Yeah. Anyway, we've got a table here. This is periodic table of the elements, selected entries of important dopants, and column 4 semiconductors. Oh, I see. So the column is how many, do you call it valence electrons? I'm not sure. Properties of intrinsic silicon. Intrinsic silicon can exist in amorphous, polycrystalline, and crystalline forms. Okay. So this is a real material science bit. Here we go, properties of doped silicon, and here's a a silicon lattice with a dope. Okay. It doesn't say what it is. Didn't we see these already? I think I remember seeing those earlier. All right. The elements boron, gallium, and indium are located in column 3 of the periodic table, shown in table 2.1, indicating that they have a valence of +3. If we dope an intrinsic silicon sample with a small amount of one of the elements in column 3, we have a crystalline structure as shown in figure 2.19. That's this one here. There we go. Experimental studies of drift and diffusion. Summary. Drift and diffusion describe the transport of charged particles in a solid. The drift mechanism defines the charged particle mobility and the resultant conductivity or resistivity of conductors, semiconductors, and insulators. A qualitative description of energy band theory was presented to obtain the number of electrons and holes contributing to the conductivity in a semiconductor. Properties of specific semiconducting materials were discussed, with particular emphasis on silicon, the most widely used semiconductor for electronic devices. By adding selected impurities in a controlled fashion, that is, by doping, either N-type or P-type material is obtained and the majority carriers are electrons or holes, respectively. This ability to modify semiconductor properties makes possible a large array of electronic devices. The sign and mobility of the charge carriers can be determined experimentally by means of the Stevenson and Keyes experiments. Other measurement techniques, especially the Hall effect technique, are widely used. All right. So we're up to chapter 3, semiconductor diodes and diode circuits. The p-n junction in equilibrium, the externally biased junction, the diode equation, practical diode characteristics, load lines and piecewise linear diode models, dynamic resistance, rectifier circuits, breakdown diode voltage regulator, diode wave shaping circuits, diode logic circuits, diode analog switch, diode capacitance and switching times, metal semiconductor junctions, photonic and microwave diodes, diode heating, SPICE model for the diode. In this chapter, we introduce the p-n junction. The p-n junction is the major part of a device called a junction diode, which is very important in its own right. However, perhaps of even more significance, the p-n junction is the basis for nearly all other solid-state devices and for integrated circuits. Thus, you need to understand the p-n junction before proceeding on to the electronic devices discussed in subsequent chapters. Figure 3.1 shows pictures of several commercial diode packages to help you visualize what a diode might look like. First, we present diode structure and physical processes which develop naturally into the diode equation. Next, we discuss diode characteristics. Representative diode data sheets are presented for comparison. Then we develop simple circuit models for the diode characteristic. We immediately present a number of common diode circuits with the dual purpose of exposing you to a variety of typical diode applications and of providing experience in the analysis of nonlinear circuits. We treat the various rectifier circuits in some detail because of their widespread use in power supplies for electronic equipment. We also consider the application of the breakdown diode to the problem of maintaining a constant voltage, but reserve the topics of active regulators, both series and switching, for study in chapter 17. Then we introduce diode limiter circuits in preparation for application as input protection for the various integrated circuits to be studied in subsequent chapters. In this section, we introduce the transfer characteristic, in which a circuit's output voltage is plotted as a function of its input voltage. The transfer characteristic is a valuable circuit analysis tool. We also present a variety of other circuits, including the diode clamp, DC restorer, diode logic gates, and a diode analog switch. Okay. So there's a few diodes here. That's an LED. That looks like a small rectifier diode, maybe a switching diode, and some bigger things. Oh, this isn't finished. After some practice on the solution of simple diode circuits, we treat the topics of junction capacitance, diode switching speeds, light emitting diodes, metal semiconductor junctions, and diode self-heating. A computer analysis of a diode circuit is illustrated using the very common circuit simulation program SPICE. A SPICE model of the diode is presented with several example programs, including a simulation of the peak rectifier circuit, which demonstrates an appropriate use of the computer where numerical iteration is involved. As you study this chapter, note that the key terms are marked in the diagram and be on the lookout for the important concepts listed below. Answer each checkup question before proceeding. Having read the material, consider the survey questions because they will help you gauge your comprehension of the material. Okay, important concepts in this chapter. Majority carriers diffuse across a PN junction in equilibrium, creating a space charge layer and a built-in potential barrier. Applying a forward bias voltage to a diode lowers the junction potential barrier and allows the diffusion current to flow from P to N. Applying a reverse bias voltage to a diode raises the junction potential barrier and allows only a very small drift current to flow from N to P. Diode current is an exponential function of applied diode voltage, Vd. Saturation current is a parameter of the diode and it doubles for a 5 degrees Celsius rise in temperature near 27 degrees Celsius. Light energy falling on a PN junction causes the saturation current to increase. Reverse bias PN junctions will conduct if the breakdown voltage is reached. An ideal diode has 0 volts drop for ID greater than 0 and 0 current for VD less than 0. A practical diode is often modeled by an ideal diode in series with an offset VF. Right, that's the forward voltage. Yeah, right. The dynamic resistance of a diode is the reciprocal of the slope of the diode equation at the operating point. Rectifiers change alternating current to direct current. Half-wave rectifiers allow load current during one half of the AC waveform, and full-wave rectifiers allow load current during both halves of the AC waveform. Peak rectifier ripple voltage is proportional to the load current and inversely proportional to the filter capacitance and the frequency. A breakdown diode has nearly constant breakdown voltage for a wide range of breakdown current and can be used to improve voltage regulation of a circuit. A clipper circuit prevents a circuit voltage from exceeding a reference voltage. A clamp circuit fixes one extreme of a waveform to some reference voltage. Diode transition capacitance varies inversely with the square root of the reverse bias voltage for an abrupt junction. Diode diffusion capacitance is proportional to diode current and minority carrier lifetime. When a diode Vd is reversed, a delay occurs before the diode turns off. Semiconductor contacts can be made non-rectifying by heavily doping the semiconductor at the interface. Schottky metal semiconductor diodes are very fast and have low offset voltage. Forward bias PN diodes can be made to emit light or to operate as a semiconductor laser. Junction heating raises junction temperature above ambient. The SPICE model for the diode allows the user to control many parameters, providing for accurate simulation of circuits containing diodes. I just want to read that again here. Metal semiconductor contacts can be made non-rectifying by heavily doping the semiconductor at the interface. I didn't really understand that. the p-n junction in equilibrium. Okay. The p-n junction is the basic building block of all semiconductor devices and integrated circuits. Some calculus there. Figure 3.3, the p-n junction in equilibrium. Okay. A p-n junction with no applied voltage at the terminals has no net junction current and is at equilibrium. Doping profiles are discussed in detail in Chapter 18. The externally biased junction. In a forward-biased p-n junction, the p terminal is positive with respect to the n terminal and current flows easily from p to n. The diode is on. In a reverse-biased p-n junction, the p terminal is negative with respect to the n terminal and only a negligible current flows from n to p. The diode is off. The diode equation, it's this monster here. The diode equation is a very important relationship for all p-n junctions. Practical diode characteristics. Reverse diode current. That's actually a pretty good diagram. If you go far enough down, it'll break. A plot of the diode characteristic with a breakdown shown at reverse voltage Vz, not to scale, so that Is may be seen. All right. The ability of a photodiode to sense light and essentially turn on a diode switch makes this an important sensor. Yeah, photodiodes. There's all sorts of photo stuff. There's phototransistors, there's photoresistors, all sorts of stuff. Note that all of the breakdown diodes in the figure 3.9 datasheet are referred to as Zener diodes according to common usage of that name. All right. Oh wow, look at that. These are the Zener diodes that I was talking about. The operating point defines the DC condition of a circuit. This condition is also called the quiescent point. Dynamic implies that the circuit is driven by a time-varying input signal, causing the instantaneous operating point to vary around the Q point. Dynamic resistance. Small signal has a specific meaning for each circuit and will be carefully defined. Small signal for a diode requires VD to be less than 5 millivolts peak. Rectifier circuits. Almost all semiconductor electronic circuits use a transformer and a rectifier to obtain 5 to 12 volt DC from the AC power line. The alternative is to use batteries, but even then the batteries might be recharged by a transformer and a rectifier. All right. The precision half-wave rectifier. The full-wave rectifier. For the same AC input voltage, the full-wave rectifier will have twice the DC output voltage of a half-wave rectifier. There it is, the full-wave bridge rectifier. What a monster. The peak rectifier. The approximate relationship of equation 3.40 is very useful. Note that Ti approximately equals 1 on F for a half-wave peak rectifier, and Ti approximately equals 1 on 2F for a full-wave rectifier. Breakdown diode voltage regulator. A piecewise linear model is one that has a transfer characteristic that is piecewise linear. Modern voltage regulators use transistors and a breakdown diode in an IC rather than standalone breakdown diodes because the efficiency of the diode circuit is low. Refer to Chapter 17 for a discussion of IC voltage regulators. Diode wave shaping circuits. We've got the clipper circuit, diode clamping circuit. This circuit is sometimes referred to as a clamped capacitor circuit. All right. Diode logic circuit. Diode analog switch. Diode logic is sometimes incorporated as a part of a more complex IC. The low-power Schottky TTL digital logic family, covered in Chapter 13, provides examples. Diode capacitance and switching times. To this point, we have considered the static behavior of the p-n junction. We now consider some capacitive effects that account for the time-dependent response of the junction to bias changes. These capacitances need to be incorporated into any high-frequency model for the diode. Okay, and we've got transition capacitance, varactor diodes. Remote operation of TV tuners often is accomplished using this principle. Okay, diffusion capacitance. Manufacturer's data for junction capacitance of the 1N4001 to 1N4007 silicon diodes. So there's capacitance in picofarads from 5 up to about 50 for different reverse voltages from 0 to 100 volts. Switching times for the junction diode. Figure D, diode current. There you go. What have we got? We've got a diode circuit. We've got a source voltage waveform. We've got excess minority carrier density. Interesting. All right, metal semiconductor junctions. Ohmic contacts. If the purpose of the metal semiconductor contact is simply to make connections to the semiconductor from the outside, we design ohmic contact. This means that the contact is not rectifying, sensitive to current direction, because no barrier potential must be overcome. To ensure ohmic contacts, the semiconductor is heavily doped in the neighborhood of the contact. In the case of aluminium to N silicon connections, this heavily doped region is called an N+ region. Heavy doping causes a high density of electrons at the metal interface so that the semiconductor takes on the characteristics of the metal and no depleted region exists. In the case of aluminium to P silicon connections, the aluminium itself, being an accepted material, can provide P+ doping to the silicon if the interface is heat treated. The distinction between an ohmic contact and a rectifying contact cannot be overemphasized. Right. The Schottky diode will be encountered again as we study the so-called Schottky transistor. All right, there's some stuff about light emitting diodes, microwave devices, diode heating. High temperatures from localized heating allow diffusion of impurity atoms, which will permanently alter the characteristics of the p-n junction. Localized heating also degrades metallization. Spice model for the diode. Some code here. This is selected diode model parameters. Wow. Saturation current, emission coefficient, parasitic resistance, zero bias p-n capacitance, p-n junction potential, p-n grading coefficient, forward bias depletion capacitance coefficient, transit time, reverse breakdown voltage, reverse breakdown current, band gap potential, IS temperature coefficient, flicker noise coefficient, flicker noise exponent. Wow. So here's example 3.14. Use SPICE to obtain the forward characteristics for 3 silicon diodes having IS equals 10 to the minus 14, 10 to the minus 13, and 10 to the minus 12 amps. Assume T equals 27 degrees Celsius, RS equals 1 ohm, and what is that? I'm not sure. Equals 1. Summary. Virtually all semiconductor electronic devices depend on the p-n junction. In this chapter, we presented the charge distribution, electric field, potential distribution, and current density across the diode p-n junction in equilibrium and with an external bias. The most important result was the derivation of the diode equation, equation 3.26, which we use to describe the one-port circuit element model for a diode. The p-n junction forms the basis for the operation of the bipolar transistor discussed in Chapter 4 and field effect transistor discussed in Chapter 5. Most important diode characteristics and specifications, including temperature sensitivity, reverse breakdown voltage, and transition capacitance, can be derived and illustrated by means of data sheets. Specialized diode devices include the LED, the breakdown diode, and the varactor diode, whose performance depends on the voltage-dependent transition capacitance. All semiconductor devices generate heat and must be removed from the area of the junction to prevent damage. An electrical analog for a thermal circuit with a power diode as a heat generator can be used to evaluate heat sink performance. We have demonstrated the graphical load line solution technique for establishing the operating point of a diode circuit with a plot of the diode characteristic. A piecewise linear model for the diode was used in the analytical solution of a number of key diode circuit applications. The half-wave rectifier, full-wave rectifier, and full-wave bridge rectifier were treated in some detail because power supply rectifier circuits are used in virtually all electronic systems. The design of breakdown diode regulators is one way to obtain a power supply with a regulated output voltage. Diode logic gates, limiter circuits, clamps, and analog switches are among the representative applications that use the switching type transfer characteristic. We expand on these ideas and applications in Chapter 13, where we will study more complex logic and switching circuits. The nonlinear characteristic of the diode is often exploited in circuits for obtaining the product of two signals. Such signals are known as mixers, modulators, or multipliers. We leave this topic for the communications texts, except to give an example in Chapter 17 as related to the phase-locked loop circuit. Although advanced photonic and microwave diode applications are beyond the scope of this text, a brief survey of these devices has been included. We also considered a SPICE model for the diode to provide examples of computer simulation of electronic circuit containing diodes. Survey questions, problems. All right, Chapter 4, the bipolar junction transistor. Basic BJT operation, volt-ampere equations for the BJT, BJT regions of operation, the common base configuration, the common emitter configuration, cutoff in the CE configuration, saturation in the CE configuration, inverse mode, CE current gain considerations, maximum ratings for the BJT, switching times for the BJT, SPICE model for the BJT. Having considered the operation of the p-n junction in Chapter 3, we are now ready to turn our attention to a device composed of back-to-back junction. The bipolar junction transistor, BJT, is the realization of a current-controlled current source. This means that we can control the current across one junction by means of a current or voltage applied to the other junction. Since their invention in 1948, transistors have revolutionized the electronics industry, displacing the vacuum tube in nearly all applications because of their size, power, service life, cost, and reliability. The p-n junction theory of Chapter 3 will apply with suitable modifications in this chapter. Here we study the operation, terminal characteristics, and simplified models of the transistor. We also present representative circuit applications, both as amplifiers and as switches. SPICE computer simulation of BJT circuits is also demonstrated. As you study this chapter, look for the important concepts listed next. Important concepts in this chapter. In an active BJT, majority carriers from the emitter are injected into the base, diffuse across the base, and are collected at the collector. The current gain, alpha F, of a BJT is that fraction of emitter current that reaches the collector. A BJT has 4 modes of operation depending on the bias direction of each of the 2 junctions. The BJT has 3 possible configurations in the circuit depending on which of the terminals is used as the reference. The common emitter DC circuit model for an active NPN BJT consists of an offset voltage of 0.7 volts from base to emitter and a controlled current source of beta FIB at the collector. The effect of collector base voltage on collector current is characterized by the Ely voltage. Okay. Ely? The dynamic base resistance R pi equals beta VT on IC. The common emitter small signal circuit model for an active BJT consists of a base input resistance R pi and a controlled current source GMVBE equals IB beta at the collector. The BJT is essentially cut off when the absolute value of BE is less than 0.5 volts. The BJT collector leakage current, ICEO, is negligible at T equals 300K, which is room temperature, but doubles with 10-degree rise. BJT collector current saturates when VCE is less than 0.3 volts. Collector power dissipation, ICVCE, produces a temperature rise of the controller junction. Okay. So this is all about BJTs. BJTs. There's a picture of one for you. NPN. A connection is also made to the substrate. External variation of the bias conditions of one or both of the junctions is what controls the action of the BJT. The inverted mode has limited application in TTL logic circuits. Common base configuration. The curves plotted in figures 410 and 411 can be obtained experimentally. Special oscilloscopes designed to plot these characteristics are called transistor curve tracers or semiconductor device parameter analyzers. Discrete NPN transistors are more common than PNP devices for a number of reasons. In integrated circuits, most of the BJTs are NPN. More will be said on this subject in Chapter 18. CB emitter characteristics, base width modulation, or early effect. I don't know. If you know, let me know. Circle model for the active transistor. The common emitter configuration. Here is our common emitter. CE collector characteristics. The parameter Ely voltage, though not a physical voltage, describes the effect of changing VCB on IC for fixed VBE. You should learn this DC model for the BJT, as it will be used throughout this text to find the operating point of a BJT. The same model is used for a PNP BJT, except VBE and ICEO are negative. AC small signal circuit model for the active transistor. The small signal condition for the BJT is thus the same as it is for PN diodes. The AC model will be used whenever we analyze the small signal operation of a BJT circuit. Emitter follower is a more descriptive term than common collector, and is often used because the emitter voltage tends to follow the input base voltage in this circuit. Saturation in the CE configuration. Figure 4.25, saturated collector emitter voltage as a function of base overdrive at 25 degrees Celsius. Figure 432, electrical characteristics and ratings for the 2N2222A transistor family, courtesy of Motorola Inc. There you go. Figure 4.34, 2N2222A characteristics showing avalanche breakdown. Collector base, collector characteristics, collector emitter, collector characteristic. Figure 435, transistor switching circuit and waveforms. A, the transistor switch, B, the input voltage, and C, the base current. And D is the collector current. There you go. Note that the rise time is defined when the collector current is rising and the collector voltage would be falling. Often, some versions of SPICE require a substrate connection for IC BJTs. Selected SPICE BJT model parameters. Transport saturation current, forward I emission coefficient, ideal maximum for beta F, corner for high current BF roll-off, forward Ely voltage, ideal maximum reverse beta R, reverse I emission coefficient, and on and on. Additional parameters that may be specified for the BJT are given in reference 6. Okay. SPICE computes beta from beta equals beta F 1 plus VCE on VA. This chart shows at a glance how the Q point changes with a change in any circuit element. Summary. Expanding on the PN junction theory presented in Chapter 3, in this chapter we developed the theory of operation, terminal characteristics, and circuit models for the bipolar junction transistor, BJT. Circuit models for the active, saturation, and cutoff regions, and for the inverted mode of operation were presented. Each model was demonstrated by means of typical circuit applications, including an overview of the design and analysis of amplifiers and switches. We have found that when unsure if the BJT is active, we should assume a model and attempt to verify it. For example, assume VBE equals 0.7 volts and IC equals beta F IB, and prove that VCE is greater than 0.3 volts. When unable to verify the active model, it is incorrect and we must assume a saturated model. Key transistor parameters needed for the circuit models, including those important for both amplifier and switching operation, were illustrated with datasheets. These datasheets will be used in subsequent chapters to develop design and analysis examples. Detailed small signal amplifier analysis is presented in Chapter 8, and detailed operation as a switch and logic gate element appears in Chapter 13. Simulation of BJT circuits by means of SPICE was discussed after introduction to some of the parameters that SPICE uses in its BJT model. All right. I think it's time for more coffee. I'm going to grab myself a coffee. All right, this is Chapter 5. I'm just going to get a fresh coffee. All right, Chapter 5, the field effect transistor. Notation and symbols, MOSFET operation, MOSFET specifications, MOS circuits, SPICE model for the MOSFET, JFET operation, JFET specifications, FET small signal models, JFET circuits, SPICE model for the JFET, MESFET operation. As mentioned in Chapter 2, the principle of using an electric field to control current flow was introduced well before the development of the bipolar junction transistor. However, practical devices based on field effect principles were not commercially available until the mid-1960s. These devices are called field effect transistors, or FETs, and operate as voltage-controlled amplifiers. FETs are referred to as unipolar devices. That is, the conduction process uses either electrons or holes, but not both, as in a BJT. The FET is used in both analog and digital circuits. See Figure 5.1. We will show that the FET has a very high input impedance that enhances its function as a good voltage amplifier. The FET is also used extensively as the basic memory or logic element in digital integrated circuits. In general, FET devices are used as amplifiers and switches, and in nonlinear circuits such as mixers. FETs fabricated from gallium arsenide in several different morphologies are used extensively in radio frequency, RF, amplifiers, and in microwave circuits. This wide range of applications does not imply that the FET will replace the BJT. As we will soon see, it really means that the characteristics are sufficiently different to provide the designer with an option not easily available with the BJT. Indeed, a growing number of ICs include both FETs and BJTs in the same circuit, BiMOS or BiCMOS technology, to take advantage of the key features of each. A number of different types of FETs are available. Their names reflect distinctive features of their fabrication processes or geometries. Figure 5.2 shows a family tree of such devices as fabricated in silicon and in GaAs, that's gallium arsenide again, for microwave applications and for high-speed digital circuits. The first commercially available FET was the junction field effect transistor, the JFET, which was first analyzed by Shockley in 1952 as basically a voltage-controlled resistor. There are two types of JFETs, N-channel and P-channel. Because the mobility for electrons in silicon is about 3 times that of holes in silicon, as I refer back to Table 2.2, N-channel devices are about 3 times faster than P-channel devices. Just going to take a quick break. So they were just saying that that the N-channel are faster than P-channel devices and have other advantages, as we will soon observe. The JFET, as its name implies, uses a PN junction to define its operation regions. If instead of a PN junction we used a metal semiconductor junction, the result is a metal semiconductor field effect transistor, the MESFET. Currently, the MESFET fabricated in gallium arsenide is used almost exclusively in microwave applications and very high-speed digital processing. This particular technology was developed in the mid-1960s but was not commercially exploited until the mid-1970s. It says here, the MOSFET, along with the BJT, is one of the most important semiconductor devices. Another key FET structure is the metal oxide semiconductor. Known as the MOSFET, sometimes referred to as an insulated gate FET or IG FET. The oxide referred to here is usually an extremely thin layer of silicon dioxide, SiO2. The MOSFET fabrication procedures lend themselves to relatively high yield, high density IC suitable for the large scale integration, LSI, and very large scale integration, VLSI, of memory and related microprocessor circuits. It is the dominant device for these types of integrated circuits. The MOSFET category is divided into a number of subdivisions that reflect key fabrication features. These are PMOS for N-channel MOS, PMOS for P-channel MOS, NMOS for N-channel MOS, CMOS for complementary MOS, BiMOS or BiCMOS for mixed mode, bipolar and metal oxide, HMOS for high performance MOS, DMOS or DIMOS, double diffused MOS, VMOS for vertical MOS, SOS-SOI, silicon on sapphire or silicon on insulating substrate, and HEMT, high electron mobility transistor. Each of the technologies has certain technical and economic advantages. For example, CMOS devices are widely used for medium speed digital high density applications and memories. SOS-SOI devices offer very high speed performance in conjunction with minimal performance degradation under exposure to ionizing radiation. BiMOS and BiCMOS, so-called mixed mode, is a process used to exploit the advantages of BJT and MOS technologies on the same integrated circuit. JFETs offer low noise performance and thus are often used as input amplifier stages in high gain operational amplifiers, capitalizing on the 5 times increase in electron mobility in gallium arsenide as compared to silicon. Gallium arsenide MESFET-based digital ICs are finding their way into very high-speed systems for primarily military and space applications. After a preliminary discussion about notation and symbols, we will consider the MOSFET. Although JFET operation is a bit easier to explain, MOSFETs by far are predominant in the industry. Consequently, we focus on the MOSFET. JFET theory will also serve as the basis for a qualitative discussion of the gallium arsenide MESFET. Several basic amplifier and switch applications are introduced, with additional applications presented in subsequent chapters. Here is the family tree of field effect transistors. So we've got FETs, we've got junction gate and insulated gate, we've got the JFET and the MESFET, and silicon and gallium arsenide, and the simple and the HEMT, and the depletion mode and the enhancement mode. And then you've got FETs with the insulated gate, depletion and enhancement, and then you've got lateral DMOS and SOI, VMOS and UMOS, dual gate and CMOS. Yeah, right. Fascinating. Important concepts in this chapter: topology and technology related acronyms and symbols, structure of a basic MOSFET, associated biasing convention, region of MOSFET operation, ohmic subthreshold cutoff saturation, difference in biasing for enhancement and depletion mode MOSFETs, definition of COX, equals epsilon O, epsilon R on D as related to MOSFET technology, derivation of the MOS ohmic and saturation regions, characteristics, definition and interpretation of key terms on a MOSFET datasheet, and the derivation and definition of MOSFET transconductance, difference between PMOS and NMOS operation, biasing, and characteristic curves, analysis and design of a basic MOS inverter with a passive resistive load, an actively loaded MOS inverter, a CMOS inverter, and MOS-based analog switches, SPICE MOSFET model and junction and syntax for model and element statements, qualitative description of JFET operation and regions of JFET operation, ohmic cutoff saturation, derivation of the JFET ohmic and saturation region characteristics, definition and interpretation of key terms on a JFET datasheet and the derivation and definition of JFET transconductance, interpretation of the Lambert turn on the ID-VDS characteristics, drain resistance definition and its measurement from the ID-VDS characteristics, JFET-based common source, common gate, common drain amplifiers, SPICE JFET model, syntax for model and element statements, qualitative topology, description and model of the MESFET. Although there are a few applications using discretely packaged FETs, most FETs are integral to VLSI or ULSI circuits. These often include over 100,000 to 1 million or more FETs on a single IC die. Wow. What they're saying there is basically CPUs are made out of FETs. CMOS, MOSFETs. Refer to Chapter 18 to more thoroughly understand how fabrication technology impacts MOSFET technologies. Enhancement mode. Although it may be confusing to the student new to the topic, the symbol is sometimes used where the drain, source, gate, and assumed substrate connection are to be inferred from the application schematic diagram. Operating in saturation for a FET is distinctly different than operating in saturation for a BJT. Talking about 3.3 volt standards there. MOSFET specifications. The list of MOS specifications are usually resident in a technology-specific computer design package. The Intel Pentium IC has over 3.1 million transistors. It uses 0.8 micrometer minimum feature size. The newer still, Intel P6, has 5.5 million transistors using 0.6 micrometer minimum feature sizes. CMOS inverter. CMOS is one of the most widely used logic families, as we will see in Chapter 13. Selected SPICE MOSFET model parameters. Model index, zero bias threshold voltage, transconductance parameter, channel length modulation, bulk threshold parameter, drain ohmic resistance, source ohmic resistance, oxide thickness, substrate doping, surface mobility. Wow. Except for analog IC input stages, JFETs are rarely used in integrated circuits. JFET specifications. Compare the JFET GM with both the MOSFET GM and the BJT GM. G for gain, I'm not sure. Drain resistance. JFET circuits, common source, common gate. Recall, a common collector BJT amplifier was called an emitter follower. SPICE JFET model parameters. Threshold or pinch-off voltage, transconductance parameter, channel length modulation parameter, drain ohmic resistance, source ohmic resistance, zero bias gate source capacitance, zero bias gate drain capacitance, gate junction potential, coefficient for depletion capacitance formula. Do not confuse beta for a JFT with beta for a BJT. Okay. MESFET operation. The basic JFET used the depletion region of a reverse bias junction to obtain a pinched off conducting channel. The junction was synthesized from p-doped and n-doped silicon. There is an entire class of JFET devices that uses a metal semiconductor junction to obtain a depletion region when operating in reverse bias. We briefly discussed this metal semiconductor junction, the Schottky diode, in section 313. This class of devices is called a MESFET, metal semiconductor field effect transistor. A simplified structure of the MESFET is shown in figure 543 down here. Simplified gallium arsenide MESFET cross section showing recessed gate and Schottky barrier depletion region. There's more in chapter 18. Summary. On the basis of a solid understanding of the PN junction and BJT, we developed the theory of operation, terminal characteristics, and circuit models for both the metal oxide semiconductor transistor, MOSFET, and the junction field effect transistor, JFET. Key relationships are summarized in Table 5.3. Even though the MOSFET is more widely used, JFET theory was covered in some detail because its operation follows most directly from the basic PN junction theory. We then demonstrated that the simplified small signal models for both MOSFET and JFET were identical, although the GM computation is significantly different. Using the simplified FET small signal model, we also demonstrated common gate, common source, and common drain amplifier operation with the JFET. There is increasing utilization of the MOSFET for amplifier application, and these topologies, which make use of active loads and the controllable W/L ratio during fabrication, are presented in chapter 8. Basically, only the biasing arrangements are changed when considering a MOSFET as opposed to a JFET, since the simplified small signal models are the same. The MOSFET finds its greatest application in logic circuits. In this chapter, we illustrated selected applications, including the basic switch, active load, and inverter. In chapter 13, we consider MOSFET logic circuits, and in chapter 15, we provide more depth in the use of MOSFETs as semiconductor memory elements. The JFET and MOSFET data sheets included in this chapter to illustrate specifications and circuit applications are used in subsequent chapters to develop design and analysis examples. Fabrication of a variety of FET devices is discussed in chapter 18. A detailed discussion of the use of gallium arsenide MESFETs in microwave and very high-speed digital circuits is beyond the scope of this text. All right. Part 2, Linear Circuits. Introduction. In chapters 4 and 5, we briefly introduced a variety of circuits with Q points located in the linear active region to obtain amplifier operation. This discussion was used to support our discussion of device operation and models. In part 2, we focus on the analysis and design of linear circuits, especially linear circuits that comprise the key building blocks of integrated circuits. In order to proceed, we introduce some key analysis tools in chapter 6. These tools include an introduction to Bode plots used to look at frequency response. Many of you are already familiar with the concept of frequency response. For example, whenever you refer to a 3 kHz bandwidth of a telephone channel, the 6 MHz bandwidth of a standard television channel, the greater than 10 MHz required for a high-definition TV, the hundreds of megahertz found in photonic optical fiber systems, or the very modest 20 Hz to 20 kHz bandwidth requirements of a good stereo sound system, you are explicitly specifying the frequency-dependent behavior of a circuit or system. Another tool we introduce in Chapter 6 is negative feedback, already implicitly invoked in Chapter 1 when we discussed the ideal operational amplifier. Virtually every circuit, integrated circuit, and system employs negative feedback to tailor operating characteristics to given specifications despite variations in device and circuit parameters. Indeed, feedback is present as a consequence of the internal topologies in semiconductor devices. You will also observe in your other electrical engineering courses that feedback concepts are employed in control systems and power systems, basically all complex electronic and mechanical systems with which you will be dealing. Additionally, in Chapter 6, these key tools are applied to non-idealities of operational amplifiers. Our application vehicle will be data sheets for two classical operational amplifiers, the MU A741 and the CA3140. Basic SPICE models are developed from these data sheets and used to illustrate the general validity of the ideal operational amplifier model from Chapter 1 and its use in negative feedback circuits. Chapter 7 includes details on establishing the Q point in the linear active region of BJT, MOS, and JFET circuits. We proceed rapidly from biasing single devices, as we briefly addressed in Chapters 4 and 5, to biasing in integrated circuits using current sources. In later chapters, particularly Chapter 10, we'll use these current sources as a necessary substitute for resistive loads in ICs because current sources effectively synthesize high resistance values which are unavailable in IC technologies. Detailed frequency-independent and frequency-dependent small-signal hybrid pi models for BJTs, MOSFETs, and JFETs based on device physics and topologies are presented in Chapters 8 and 9, respectively. These models are employed to study the properties of basic single-transistor circuits. Depending on the level of algebraic complexity, we will use SPICE to support our analysis and design efforts. The Bode plot is our principal vehicle for presenting frequency-dependent behavior. Multi-stage amplifiers are also studied. The differential amplifier, employing either emitter or source-coupled pairs, found in virtually all ICs, is presented in Chapter 10. Models and circuit results from Chapter 8 are combined with Chapter 7 current sources to obtain circuits using a minimum number of resistors and no coupling or bypass capacitors. The device matching and specification tracking inherent with basic semiconductor technology is important to meet the required high-performance specifications. It is also interesting to note that many of the circuits in Chapter 10 are used in digital IC families. This aspect is explored in Part 3. Although we introduced basic feedback concepts in Chapter 6, we did not apply them to individual circuits. In Chapter 11, we apply feedback to amplifiers. A key task will be to identify which of the four basic topologies best describes a particular configuration. Key circuit performance characteristics are dependent on which of the four topologies are employed. When we consider the frequency response of multi-stage amplifiers, we must be concerned about stability. An amplifier might be very stable at low frequency, where the phase of the feedback signal is negative, but become unstable at higher frequency, where the phase of the feedback signal changes. Indeed, we may deliberately design a circuit to have positive feedback at some frequency in order to obtain an oscillator, that is, become a signal generator whose output is no longer controlled by an input signal. Virtually all electronic systems require an oscillator which serves as a signal source. For example, a figure of merit for computer is the clock rate. That is, the clock is an oscillator. We discussed several typical oscillator designs in Chapter 11. The concepts presented in all of the preceding chapters, supported by SPICE, are used in Chapter 12 to perform a detailed circuit design of an operational amplifier using a BJT array, followed by a detailed analysis for the MU-A741 and CA3140. Other common linear ICs, including voltage regulators and analog multipliers, are also discussed, as are trends in linear IC performance. Chapter 6, Basic Analysis Techniques, Operational Amplifier Specifications, General Feedback Concepts, Bode Magnitude and Phase Plots, and then that's it. Two basic tools are discussed in this chapter: techniques for analyzing frequency-dependent circuits and systems, and negative feedback. Expanding on the ideal operational amplifier concepts presented in Chapter 1, we apply both of these tools to non-ideal operational amplifiers. It is important to understand that even though we will focus on operational amplifier circuitry and applications, operational amplifiers usually comprise only a small, albeit important, portion of any electronic system. However, the circuit's combinational topologies and analysis and design techniques are sufficiently universal that a detailed study of the operational amplifier in this chapter and in Chapter 12 will allow us to extend these concepts to many other analog and digital integrated circuits and systems. Furthermore, we will use the ubiquitous MU-A741 as our tutorial analysis vehicle. Early versions of the UA741 operational amplifier were introduced in 1966, and in the ensuing decade it became one of the most widely used ICs. Since then, literally thousands of operational amplifiers have been introduced as either standalone ICs or as part of a larger IC. Many of these standalone operational amplifiers are designed with special features, but it is interesting to observe that many of the newer designs advertise their pin-for-pin compatibility with the UA741. The UA741 is a BJT-based integrated circuit. Our tutorial vehicle for operational amplifiers with a MOS input stage is the CA3140. As with the MU-A741, the CA3140 represents a mature technology and design whose performance has been superseded. Important concepts in this chapter: ideal operational amplifier criteria, reading and interpreting an operational amplifier datasheet, definitions of input offset voltage and current, input bias current, input resistance, large signal voltage gain, output resistance, and output short circuit current, frequency independent and frequency dependent SPICE models for the operational amplifier, summing point constraint applications, basic feedback system block diagram, figure 6.9, negative feedback, definitions of loop gain, open loop gain, and closed loop gain, use of negative feedback for gain stabilization and distortion reduction, definition of numerical manipulation of the decibel, construction of the Bode magnitude and phase plots, computation and identification of the -3 decibel response point, Bode magnitude and phase plots for a single pole low pass filter and for a single pole high pass filter, SPICE AC analysis of the single section low pass and high pass filters, Bode plot magnitude and phase errors compared to the actual transfer function plots, Bode magnitude and phase plots for a bandpass filter, use of negative feedback for broad banding, definition of the gain bandwidth product, approximations for systems having a multi-corner frequency response. Input stage, often a differential amplifier, as discussed in Chapter 10. The intermediate section provides a large voltage and/or current gain. The output section provides impedance matching to driver load. These data sheets and models are resident in many CAD programs, including more advanced version of PSpice. Also, many manufacturers offer data sheets on computer diskettes and CD-ROMs, as well as on the World Wide Web. PSpice has a number of internally available libraries. For the time being, it is useful to just use simplified models. Refer to problem 659 for a somewhat more accurate two-port SPICE model. We will show feedback elements in blue throughout the text. It's the data sheet for the CA3140. General feedback concepts. This is the one diagram EE students should never forget. There you go. This is the basic feedback system. Sensitivity analysis on a component-by-component basis is built into SPICE. Note we will now use phasor notation. If you have not yet been introduced to the concept of a pole in your basic circuits courses, you can substitute the term section for pole in the usage in this chapter as it relates to filters. Broadbanding. We are now in a position to combine feedback concepts with a frequency response analysis. Okay. A more accurate frequency-dependent model, less subject to loading, is shown in problem 659. SPICE really shows its computational worth in analysis and design of multi-corner circuits. It should be obvious that in a multi-stage circuit, the frequency response characteristics will be complicated. However, usually what we really need to know for a given design is the location of the overall 3 decibel down response points, as illustrated in figure 629. The circuit behavior above omega H1 and below omega L3 is of relatively minor importance. In general, it is possible to represent this characteristic in this form, and off we go with some mathematics, which we're not going to look at closely. Summary. Key analog integrated circuit and system design and analysis tools were presented. We first focused on the data sheets for a bipolar and a BiMOS operational amplifier. You should be able to read and interpret data sheets. Using these data and the basic operational amplifier model, a simplified two-port SPICE model was synthesized and demonstrated. Currently, many of the larger IC manufacturers have provided detailed circuit-based SPICE models for their products. We study these circuit designs in Chapter 12. As mentioned previously, virtually all analog ICs, whether considering their internal circuit design or their use in small or large systems, employ negative feedback. In this chapter, we derived and exploited the key equation given there for use when using operational amplifiers for a variety of applications. Applying summing point constraints of VI equals 0 and II equals 0 allowed us to design with resistor ratios, thereby ignoring the large active device-based parameter variations found in integrated circuits. We also observed that negative feedback is useful to linearize the IC transfer function. Additional feedback concepts are applied to circuit designs in Chapter 11. Virtually all systems have, by design or otherwise, frequency-dependent behavior. A common approach to show this behavior is by use of Bode, magnitude, and phase plots. Indeed, the key output representations from SPICE AC analysis are magnitude and phase plots. which are directly related to the asymptotic Bode plots. We presented the derivation of two key functional forms, the single-pole low-pass, high-pass filters. Although SPICE can provide frequency response information for complex circuits and systems, it is important for the reader to understand and interpret the results of using transfer functions and equivalent circuits. The frequency-dependent behavior, along with feedback, was included in the analysis of ideal and non-ideal operational amplifier-based circuits. Indeed, the focus of many of the chapter problems combines operational amplifiers with external frequency-dependent networks in a negative feedback loop. The analytical designs are to be supported by SPICE. The GBW was also introduced as a metric to compare system performance. Now that we have studied the terminal characteristics of operational amplifier integrated circuits, we will proceed to study the individual internal circuits and their design in analog integrated circuits, including frequency response. We then return to use feedback with these circuits in Chapter 11 and combine the results in Chapter 12 by analyzing the internal circuitry of several analog ICs, as well as by designing our own basic operational amplifier. Table 6.3 summarizes some properties of common operational amplifiers. There we go. Selected properties of some common operational amplifiers. So we've got BJT, JFET, MOSFET, BJT, and then FT, IB, and RO. Survey questions, problems. Biasing and stability. Chapter 7. BJT Q point selection, BJT Q point stabilization, FET bias and stabilization, BJT current sources, MOSFET current sources. As we continue the study of transistor amplifier circuits, it is necessary to consider the DC bias circuitry that is used to establish the Q point. Of course, we expect the operation of a linear amplifier to be in the active region, as explained in chapters 4 and 5. Since selection of the Q point affects the AC parameters of the transistor, it is not an arbitrary decision in amplifier design. Furthermore, this operating point must be maintained within limits as the DC parameters of the transistors vary, either with temperature or because of manufacturing variations within the same device type. Make the exact values uncertain. We present design criteria for Q point selection and stabilization, both for bipolar junction transistors, BJTs, and for field effect transistors, FETs. Resistive bias circuits are investigated first because they are easily understood and are used to construct test circuits and simple low-volume analog circuits. Aspects of bias stabilization, such as the benefit of an emitter resistor, carry over into integrated circuit design. Integrated circuits must be biased without large resistors or large capacitors, which cannot be integrated economically, if at all. For ICs, a transistor is usually cheaper than a resistor and much cheaper than a large capacitor. As a consequence, active current sources are used instead of resistors. Current sources are presented as the second topic in bias. Their use is described in chapters 8 through 13. Power amplifiers have a third type of bias arrangement that is used to avoid wasting power. This topic is discussed in chapter 10. Important concepts in this chapter. BJT and FET Q points must be selected such that device maximum rated values are not exceeded. The Q point for each active device of an amplifier must be chosen such that the dynamic Q point remains in its linear region at the desired signal level. The bias network of an amplifier must not load the signal source excessively. Q points are selected to obtain desired small signal parameters. An effective way to stabilize BJT and FET cue points for changes in parameters is by the use of an emitter resistor or a source resistor, respectively. Two or more active devices can be accurately matched in parameters on a die with IC technology, and temperatures also tend to equalize on a die. Two active devices and a reference current can produce a stable current source equal to the reference current with a high output resistance. A Widlar current source produces a current smaller than the reference current and has somewhat higher output resistance than a simple current source. A Wilson current source has a very high output resistance. MOS current sources use another FET to provide the reference current. BJT cue point selection. AC considerations. The purpose of the amplifier circuit is to develop an appropriate voltage across or current through some particular load resistance. Thus, the application usually determines RL. The MOSFET will have essentially no gate current at any temperature, assuming maximum gate voltage is not exceeded. SiO2 is an excellent insulator. If the areas of the BJT junctions are made different, the resulting currents will be different in the same ratio, since IS is proportional to area. The assumption of equal temperatures is dependent on thermal resistances of the die and power dissipation, so this assumption is approximate. Summary. In this chapter, we presented design criteria for establishing the cue point for both BJT and FET single transistor circuits. We used DC and AC load line analysis to locate the cue point in the linear regions required to obtain amplifier as opposed to switching operation. The bias circuit design must take into account maximum power, voltage, and current ratings for the particular BJT and FET. Fabrication technology results in a wide range of device parameters. In this chapter, we considered these variations by studying the cue point bias stabilization. Bias stabilization was our introduction to negative feedback, a concept we study in considerable depth in Chapter 11. Discrete circuit biasing and integrated circuit biasing design techniques are different because of the design requirements for IC fabrication technologies. Transistors are much more economical to use than large value resistors, and capacitors are all but forbidden. The simple Widlar and Wilson current sources accommodate these constraints. Both BJT and MOSFET current sources have widespread application in monolithic circuits. Even though these current sources are more complex, they offer advantages over resistor biasing with respect to impedance levels and stability. In Chapter 10, we use current sources as active loads to achieve amplifier performance not practically realizable with discrete component design approaches. Table 7.1 compares several current mirror circuits. These current ratios are also directly affected by the ratios of the device areas. I might actually start calling out the suggested readings. I haven't been doing that, but I will just for the rest of the book. I won't tell you the order. I'll just give you the name of the book or the paper. CMOS Analog Circuit Design, Analysis and Design of Analog Integrated Circuits, Bipolar and MOS Analog Integrated Circuits. Oh, that's it. Actually, I won't read them out. It's all right. Chapter 8, Small Signal Mid-Frequency Amplifier Analysis, the Hybrid Pi Model, the Common Emitter Amplifier, Impedances and Amplification, Common Base Amplifier, Impedances and Amplification, the Emitter Follower Amplifier, Impedances and Amplification, the FET Model, MOSFET Amplifiers with Active Loads, Discrete Cascaded Amplifier Stages, Direct Coupled and Bi-CMOS Amplifiers, Measurement of BJT Hybrid. Having considered the establishment of an acceptable Q point in the active region by proper bias design, we are now ready to analyze transistor circuits using a linear model. In this chapter, we define small signal amplifiers as those in which the input-output transfer characteristic is approximately linear. This means that for the BJT, VBE is less than VT. For the JFET, VGS is less than VGS minus VP, and for the MOSFET, VGS is less than VGS minus VT. Some absolute values in there. See problem 818 at the end of the chapter. For large signals, graphical analysis and the SPICE transient analysis are more appropriate, since it is not proper to assume a linear model if the parameter change as the signal varies. In spite of this, however, a linear model is sometimes used in large signal analysis as a simple means of obtaining very approximate results. Further, we restrict our consideration here to mid-frequencies. You've got a note here. Most amplifiers have a mid-band range of frequencies where amplification is not attenuated by series impedances or of coupling or bypass capacitors, or by shunt impedances of parasitic capacitances. The concept of impedance demands a sinusoidal signal. I didn't know that. This means that our models neglect those parasitic capacitance associated with the transistor junctions, which usually begin to affect the circuit operation above several tens of kilohertz. It also means that we neglect the capacitive reactances of the coupling and bypass capacitors, although they do have an effect below some frequency. After reviewing the small signal AC model of section 4.5, we consider certain refinements to better model second-order effects. We will apply this model to a combination of various features of CE, CB, and CC amplifiers. We will also apply the small signal field effect transistor, FET, model to the variations in FET amplifier configurations. High-frequency models are treated in Chapter 9, as is the frequency dependence of the amplifiers. After first considering simple discrete transistor amplifiers, we turn to multi-stage integrated circuits. ICs avoid the use of capacitors by direct coupling of amplifier stages, and they often use active loads. Direct coupled BJT and metal oxide semiconductor FET amplifiers are discussed to demonstrate this technology, along with a combination of the two called BiMOS or Bi-CMOS. Differential amplifiers are covered in Chapter 10. Included is a section on the measurement of BJT common emitter hybrid parameters and how the hybrid pi parameters are obtained from them. Important concepts in this chapter. Parasitic capacitance and the reactance of coupling and bypass capacitance are ignored at mid-band frequencies. The BJT hybrid pi model is a linear model that realistically represents the BJT at one Q point for small signals. The fixed resistance from the active base region to the base contact is RB. The parameter RPi models the dynamic resistance of the forward biased base emitter junction. The base narrowing due to the early effect is modeled by a feedback resistance RMU, which is usually large enough to neglect, and an output resistance RO, is it? RO maybe? The small signal model for a FET has no drain to gate feedback conductance. The transconductance of a BJT is higher than that of the FET of the same chip area. Either enhancement or depletion MOSFETs are used as active loads for CS FET IC amplifiers because they use much less chip space than resistors. The voltage amplification of IC FET amplifiers is controlled by the W/L ratio of the devices. CMOS technology can produce large voltage gains using a PMOS current mirror for the active load of an NMOS CS amplifier. Cascaded amplifier stages are analyzed by using the input resistance of the last stage as the load resistance of the preceding stage. I'm going to read that again. Cascaded amplifier stages are analyzed by using the input resistance of the last stage as the load resistance of the preceding stage. Direct coupled circuits are used in IC design, avoiding coupling capacitances. The BJT cascade amplifier is a CE stage directly coupled to a CB stage. By CMOS IC combine the best features of BJT and CMOS devices on one die. And then there's a table with different types of amplifiers and their properties. The hybrid pi model. Figure 8.1a recalls the small signal model for the BJT developed in section 4.5. You're reminded that linearity requires that VBE is less than VT at room temperature where VT equals 26 millivolts. The major difference between the models of figures 8.1 and 8.2 is that when RB is considered the control voltage, V pi not equals VBE, the difference is usually only a few percent. Topologically, the common source FET amplifier is analogous to the common emitter BJT amplifier. For this discussion, it makes little difference whether we use a JFET or a MOSFET. The small signal models are there's a word missing there, probably are the same. The common drain amplifier is often called a source follower, analogous to the BJT emitter follower topology. Summary. Basic amplifier operation was introduced in earlier chapters. The material in this chapter built on the basic BJT operation described in chapter 4, the basic FET operation outlined in chapter 5, and the biasing discussed in chapter 7 to develop a small signal model that was used to complete a mid-frequency amplifier analysis. Both the common emitter hybrid and the hybrid pi models were defined with typical model element values obtained from actual device datasheets. The BJT and FET are modeled as two-port devices that can be connected in three basic configurations. We analyze each of the three configurations: common emitter, common source, common base or gate, and common collector or drain, to determine the properties of amplification, input resistance, and output resistance. Tables 8.1, 8.2, and 8.3 summarize these results. MOS integrated circuits use active loads to realize a larger effective resistance without the sacrifice of chip space required by diffused or implanted resistors. Bipolar ICs also use active loads. We considered several examples of such design, but have reserved differential amplifiers for Chapter 10. Cascade amplifiers are used for achieving higher amplification than is possible in a single stage and for input-output matching. We have considered an amplifier design using capacitance-coupled discrete transistors and also direct-coupled transistors as used in monolithic design, where coupling capacitors are avoided. Included were examples of combination bipolar and MOSFET devices, such as found in BIMOS circuits. In chapters 10 through 12, we study multi-stage amplifiers as they are implemented in the design of operational amplifier ICs. Chapter 9. Frequency effects in small signal amplifiers. High-frequency small-signal BJT and FET models, the effect of CMU and CGD, the Miller effect, small-signal amplifier low-frequency analysis, direct-coupled and bi-CMOS amplifier examples. In Chapter 8, we developed and used simplified small-signal models to compute key characteristics of a variety of BJT and FET amplifier circuits. All of these models and circuits were assumed to be frequency independent. Topics in Chapter 9 include the addition of parasitic capacitances in the models that will affect the high-frequency performance and the consideration of the effects of coupling and bypass capacitors on the overall circuit. As in Chapter 8, we discussed amplification of BJT and FET circuits, but now with frequency dependence added. To tackle the analysis and design of frequency-dependent circuits, we need to introduce simplifying techniques for looking at complex circuitry. Without some of these techniques, it would be easy to lose insight into the overall operation because of algebraic complexity. The Bode plot tools of Chapter 6 are used here extensively. The parasitic capacitance between the input and output nodes of an inverting amplifier is effectively increased by the voltage amplification of the amplifier. This result, known as the Miller effect, is analyzed in this chapter, and a strategy is presented to simplify the analysis of such circuits. After a brief familiarization with the effects of the parasitic capacitances on the active devices in typical amplifier circuits, we demonstrate the power of a SPI simulation in an analysis or design situation. Important concepts in this chapter. The basic active IC BJT has 3 junction capacitances: the base emitter C-pi, the base collector C-mu, and the collector substrate CCS, of which C-mu and CCS are depletion region capacitors across reversed bias junctions. The active base emitter junction is forward biased, and effects of C-pi include a depletion layer capacitance and a base diffusion capacitance. All FET structures have gate source CGS, gate drain CGD, and junction capacitances to the substrate. Both BJT and FET high-frequency performance can be characterized by unity gain frequencies. The Miller theorem allows capacitance between the input and output of inverting amplifier to be replaced by a larger capacitance at the input. This allows us to compute a quick estimate of the overall bandwidth of the circuit. Bode plots facilitate the combination of the frequency responses of mid-band, high-frequency, and low-frequency models of amplifier circuits. Each parasitic capacitance in the high-frequency model of an amplifier circuit introduces a high-frequency corner in the frequency response of the circuit. Each coupling and bypass capacitor in an amplifier introduces a low-frequency corner in the frequency response of the circuit. Direct coupling between stages in an IC is used to avoid the need for coupling capacitors, which are not economically produced in monolithic technology. The devices in a cascade amplifier are arranged to minimize the effect of the parasitic capacitances. This is a great advantage in high-frequency circuitry. Distributed models used for very high frequencies are microwave models and microwave models are beyond the scope of this text. That's figure 9.1, idealized cross-section of an NPN bipolar junction transistor showing parasitic elements. Similar physical concepts are valid for a PNP transistor. That's cool. Summary. In earlier chapters, BFT and that's BFT, I think it means BJT, and FET models and circuits were assumed to be frequency independent. In this chapter, small signal voltage dependent capacitance inherent with junction behavior in both the BJT and FET were added to the basic frequency independent hybrid pi mode. These capacitances, in particular C mu and CGD, have a significant effect on the amplifier frequency dependence. Characterization of the frequency-dependent behavior is obtained by the use of Bode, magnitude, and phase plots. This graphical approach is almost universally used for describing circuit behavior. We also use Bode graphical analysis in Chapter 11, where we discuss feedback, amplifier frequency response, and stability compensation. Algebraic complexity is significant in frequency response analysis. Consequently, simplifying techniques, including the Miller approximation, were demonstrated in this chapter. Classical resistance, capacitance, coupled common emitter and common source amplifier circuits at high frequency were treated first to emphasize the effects of parasitic capacitance in a single-stage amplifier without undue complexity. Next, low-frequency circuit behavior resulting from emitter and source bypass capacitors and coupling capacitors was demonstrated. Modern IC design using direct coupling to avoid capacitors was presented. Active loads and bi-CMOS designs were considered. Finally, examples incorporating both high and low frequency response characteristics were also given. These multi-gamma frequency responses are best analyzed by means of circuit analysis computer programs such as SPICE. The subject of differential amplifiers is reserved for the next chapter. The general subject of feedback, where a sample of the output is inserted at the input in order to control the amplifier characteristics, is reserved for Chapter 11. Survey questions, problems. Chapter 10, Operational Amplifier Circuitry. Differential BJT amplifiers with resistive loading, differential MOS amplifiers with resistive loading, differential JFET amplifiers with resistive loading, BJT amplifiers with active loading, MOS amplifiers with active loading, power output stages, effects of device mismatch. As discussed in Chapter 1, operational amplifiers are multi-stage circuit configurations, especially amenable to integrated circuit technology. They are usually characterized by high voltage gain, high input impedance, and low output impedance. However, many specialized configurations exist, and in this chapter we examine the design and application of these composite circuits. Generally speaking, an operational amplifier consists of one or more differential or difference amplifiers, multiple current sources used for biasing and active loads, power amplifiers for output circuit drive capability, and general single-ended amplifiers for achieving voltage gain and DC level shifting. In this chapter, we examine all of these classes of circuits as they apply to the design of an integrated circuit. In section 10.1, we introduce the emitter-coupled differential amplifier with resistive loads. Resistively loaded metal oxide semiconductor MOS amplifiers are examined in section 10.2, followed by resistive loaded JFET amplifiers in section 10.3. Using material related to current sources in Chapter 7, the resistive load will be replaced by a modified current source, and in that configuration we will call it an active load. BJT and MOS actively loaded amplifiers are discussed in sections 10.4 and 10.5 respectively. Section 10.6 treats Class B power output stages. The term power is used rather loosely in that for integrated circuits we rarely consider power levels over several hundred milliwatts. The discussion, however, is still applicable to audio power amplifiers using larger discrete devices such as those used in consumer audio products. We cover the effects of device mismatch in differential amplifiers in section 10.7. SPICE simulations and related discussions are then applied to a variety of examples from earlier sections of this chapter. Using the basic circuit configurations, definitions, and specifications in this chapter, we will proceed to chapter 12 in chapter 12 to the analysis and design of some typical analog ICs. Important concepts in this chapter. Resistively loaded emitter-coupled pair circuit topology, definitions of input differential voltage and output differential voltage, emitter-coupled pair DC and AC analysis and design, half-circuit analysis technique, derivation and interpretation of the IC1 and IC2 and VOD versus VID transfer functions, common mode gain and common mode rejection ratio, CMRR, current source biasing, differential mode and common mode input resistance, resistively loaded MOS source coupled pair circuit topology and DC and AC analyses, resistively loaded JFET source coupled pair topology and DC and AC analyses, actively loaded BJT circuit topologies and DC and AC analyses, actively loaded emitter-coupled pair circuit topology and DC and AC analyses, actively loaded MOS amplifier topologies and load line and DC analyses, definition of Class A, B, and B power amplifiers, Class B power amplifier circuit topology and large signal transfer function, crossover distortion, Class AB power amplifier circuit topology and large signal transfer function, biasing design of Class AB power amplifiers, back-to-back load line analysis, Class A power amplifier circuit topology and large signal transfer function, output power and efficiency definitions, Class A, B, and B amplifier power and efficiency, short circuit protection, harmonic distortion definition and computation, effects of input differential voltage offset voltage mismatch, collector load resistor mismatch, and input offset current mismatch. Summary. Virtually all analog circuits are composed of a combination of differential amplifiers with passive and active loads, single-ended amplifiers with active and passive loads, current sources, and some type of output driver. Current sources were presented in Chapter 7. The focus of this chapter was on amplifiers with a particular emphasis on the differential amplifier. We initially studied the emitter-coupled and source-coupled pair with passive and active loads. Although the DC equivalent circuits and device models are significantly different, we found that the AC equivalent circuits were virtually identical. Of course, the computation of GM for BJT and FET are quite different. The common mode and differential mode voltage gain and input resistance calculations were simplified by use of the half-circuit model approach. Technological constraints rule out large value resistors for IC implementations. Consequently, the effective large output resistance of the current source is used as an active load in both single-ended and emitter-coupled amplifier circuits. Very large voltage gains using only transistors were demonstrated. Classes A, B, and AB power output amplifiers were presented. The large signal analysis of the Class B amplifier led to a derivation of the transfer function. Crossover distortion was eliminated by using two series diodes to force a low level of Q-point collector current in the output transistors. This is the Class AB circuit, which dominates in analog integrated circuits. The Class A amplifier is also often used as an emitter-follower output stage. In general, Class B and AB operations are more efficient than Class A operation. However, Class A operation usually exhibits less harmonic distortion than Class B or AB operation. Because the power output stages are usually configured as emitter followers, they are subject to destructive overloads if the output is short-circuited or connected to an unreasonably low load resistance. Output current limiting circuitry to protect the output transistors was therefore discussed. IC fabrication technology yields closely matched circuit elements. However, slight variations do occur, and the effects of device mismatch were studied in the emitter-coupled pair. These device mismatches are modeled as an input offset voltage and input offset current. Having introduced the differential amplifier and the power output amplifier, we will analyze several typical IC operational amplifiers and a related analog IC comparator in Chapter 12. Chapter 11, Feedback. Overview of general feedback concepts: voltage shunt feedback, current series feedback, voltage series feedback, current shunt feedback, amplifier frequency dependence and compensation, oscillators. As discussed in earlier chapters, the properties of an amplifier or any circuit are subject to the inherent fluctuations in active device parameters, whether due to manufacturing tolerances, power supply, voltage fluctuations, temperature, or aging. In addition, the transfer characteristic of a BJT or FET is nonlinear. Although we can study the performance of a circuit using a linear small signal model, the model is at best an approximate approach. As presented in section 6.2, we introduced the use of feedback to improve these performance characteristics. Basically, feedback is the incorporation of a sample of the output signal at the input to modify the performance of the circuit, or of a circuit. The topic is further divided into two categories: negative feedback and positive feedback. The terms negative and positive refer to the phase relationship between the output and input signals when they are combined. As demonstrated in section 6.2, negative feedback, often with the adjective negative omitted, is used to 1. Stabilize the gain of an amplifier, 2. Reduce distortion, 3. Increase bandwidth, and 4. Modify the input and output impedances. In this chapter, we focus on the details of incorporating feedback in a circuit. Section 11.1 is a brief overview of key equations and concepts from Section 6.2. Section 11.2 through 11.5 introduce each of the four basic feedback circuit configurations: voltage shunt, current series, voltage series, and current shunt. Each section provides a demonstration of the modification of input and output impedance and gain stabilization in general two-port configurations, as well as circuit examples. One of the chief difficulties encountered when designing feedback into a circuit is the possibility that the phase relationship between the input and output signal will change with frequency, resulting in the feedback becoming positive so that the circuit will become unstable. Unstable in this context means that the circuit does not perform as an amplifier but as an oscillator, that is, a signal source at a given frequency. Amplifier stability is studied in section 11.6, and an overview of oscillators is given in section 11.7. Important concepts in this chapter. Okay, we've got some expressions there. Voltage shunt, parallel input, parallel output, transresistance, amplifier feedback, block diagram, gain, input impedance, output impedance, Y parameter, two-port representation, and unilateral network approximations, single-stage CE amplifier and multi-stage amplifiers with resistive, voltage shunt feedback topology, and computation of A, Ri, and Ro. Voltage shunt analysis of the operational amplifier and other multi-stage amplifiers, current series, series input, series output, transconductance, amplifier feedback, block diagram, gain, input impedance, output impedance, Z parameter, two-port representation, and unilateral network approximations, computation of A, Ri, and Ro for the single-stage CE amplifier and multi-stage amplifiers with resistive current series feedback, emitter degeneration, voltage series, series input, parallel output, voltage amplifier feedback, block diagram, gain, input impedance, and output impedance, H parameter, two-port representation, and unilateral network approximations, multi-stage amplifiers with resistive voltage series feedback topology, current shunt, parallel input, series output, current amplifier feedback, block diagram, gain, input impedance, output impedance, G parameter, two-port representation, and unilateral network approximations, multi-stage amplifiers with resistive current shunt feedback topology, properties of feedback amplifiers where A is alpha is a function of frequency, which includes positive feedback and closed loop gain stability, gain margin and phase margin, compensation and dominant frequency, definition of an oscillator and Barkhausen criteria, RC phase shift and Wien bridge oscillator topologies, analysis and design, LC oscillator topologies, general circuit, Colpitts circuit, Hartley circuit, definition of the piezoelectric effect and the impedance characteristic of a crystal, properties of a crystal-controlled oscillator with examples. Wow, that's a lot of topics. The Miller effect was derived and discussed in Chapter 9. Note that the Miller effect is evident in any BJT or FET circuit, any two-port, where we include a CF or a more complex feedback network. One cannot overemphasize the importance of using resistor ratios as a consequence of employing negative feedback for amplifier circuit designs. Often this approach is called design by ratios. Advanced circuit theory and control system courses discuss stability in the context of equation 11.116. The inherent nonlinear operation of oscillators results in real oscillators not having an ideal single frequency operation but a spread of frequencies around the dominant frequency. Summary. The use of negative feedback in an individual circuit around an operational amplifier or in a complex electronic system is one of the most important techniques for stabilizing the performance against the inherent variations in active device parameters. We first observed that negative feedback was used to stabilize gain, reduce distortion, and increase bandwidth in Chapter 6, and then used it to modify input and output impedances in this chapter. By treating the feedback system as an interconnection of two-port networks, we obtained four fundamental interconnections. They were denoted as voltage shunt, transresistance, current series, transconductance, current shunt, current, and voltage series voltage. Table 11.1 summarizes the overall two-port results. After completing general gain and impedance derivations using basic two-port circuit theory, single and multi-stage circuits incorporating negative feedback were analyzed. To minimize algebraic complexity, model and circuit simplifications were used. We observed that, in the limit, the gain is dependent only on the feedback network, which is often composed only of a simple set of passive components, usually resistors. In order to solve for the key features of a feedback amplifier, 1. Identify the type of feedback being used. 2. Draw the small signal model with the feedback network separately identified. 3. Compute the appropriate two-port Y, Z, H, or G parameters for the feedback network. 4. Include the feedback network two-port parameters in the small signal model as input and output circuit loading and as a feedback generator. Do not include the feed-forward generator term. 5. Solve for the appropriate A of the resultant small signal model. Use all suitable approximations. Include the feedback network loading and set of feedback generator term to 0. Observe that the forward network two-port parameters are not required for obtaining A. 6. Substitute the result for A and F into A equals A on 1 plus AF. Use Thevenin and Norton transformations to solve for voltage gain if required. One of the most important applications of negative feedback is its use with an operational amplifier. This application as a voltage shunt two-port configuration was presented. This reinforced our work in chapters 1 and 6, where we used the ideal operational amplifier characteristics along with the summing point constraint analysis technique to introduce key configurations such as the inverting amplifier, non-inverting amplifier, buffer, and active low-pass filter. Because any real circuit has a frequency-dependent gain, we inadvertently introduce additional phase shift into the circuit, which could result in a positive feedback condition. This phase shift could lead to instability, which means the circuit would function as an oscillator rather than an amplifier. These effects of frequency response were presented along with a methodology for providing compensation, thereby stabilizing the circuit. Oscillatory behavior is a desirable function in its own right. By adding additional predictable phase shift to a circuit, we obtain positive feedback and oscillator operation. Several configurations include the RC phase shift, Wien bridge, general LC, Colpitts, Hartley, and crystal-controlled oscillator configurations were presented. Table 11.2 summarizes the key properties of general sine wave generation techniques. Although the general feedback concept is straightforward, its application to real circuits and systems is algebraically complex. Indeed, for oscillators, the problem is nonlinear. However, the two-port approach presented in this chapter offers an algebraically tractable technique for working with these circuits if you can identify the feedback network. As demonstrated, SPICE is a useful tool in analyzing and designing these complex circuits. All right, I'm going to make more coffee. Chapter 12, Operational Amplifier Examples. Design of an operational amplifier using a CA3096 NPN PNP transistor array. Analysis of a MU-A741 operational amplifier. Analysis of a CA3140 operational amplifier. The LM111 comparator. Trends in operational amplifier performance. Using the fundamental circuits derived in Chapter 10, we are now in a position to design and analyze the internal circuitry of complete operational amplifiers and related analog integrated circuits. To avoid getting lost algebraically in multiple transistor circuit analysis, we will make a deliberate effort to look for simplification, such as neglecting base currents and then following a systemic approach. The approximate approach will be supported by a SPICE computer simulation. This approximate approach, there's a note here, the analysis approach is independent of the technology or type of circuit. Okay, this approximate approach is divided into three segments. 1. Qualitative analysis. The idea here is to identify key circuit functions such as amplification, voltage level shifting, current sourcing, and active loading associated with a given transistor. 2. DC circuit analysis. The goal is to compute approximate values for all important quiescent currents and voltages. 3. AC circuit analysis. Using results from DC analysis, the small signal voltage gain, input resistance, and output resistance are computed. Phasor notation is used. To demonstrate these procedures, we design a simple operational amplifier using a CA3096 NPN PNP transistor array. The design is verified using a SPICE simulation. We then apply this analysis approach to several analog circuits. Although the BJT-based MU-A741 general-purpose operational amplifier, the CA3140 BIMOS operational amplifier, and the LM111, 211, 311 BJT-based comparator have been superseded by ICs with much higher performance, it is useful pedagogically to use these circuits for an initial exposure to the basics of the internal circuitry of analog integrated circuits. Another motivation was that circuit diagrams and supporting material are readily available. We compare our approximate and SPICE analyses of a MU-A741 general-purpose op-amp with specifications given by the manufacturer's data sheet first introduced in Chapter 6. In Section 12.3, we present an analysis of a CA3140 MOSFET input MU-A741 pin-compatible operational amplifier. Closely related to the IC amplifier is the comparator, so we devote Section 12.4 to the analysis of the LM111, 211, 311 family of general-purpose comparators. Abbreviated versions of the data sheets for all of these ICs are included. Section 12.5 includes an overview of trends in operational amplifier performance and how this performance compares to the MU-A741 and CA3140. References are also given to a variety of manufacturers of analog ICs. Many of these manufacturers not only provide computer-based data books but complete SPICE models for use in incorporating their products. System design. These data are also often available on diskette, CD-ROM, or through home pages on the Internet's World Wide Web node. Important concepts in this chapter. Design of a 5-transistor operational amplifier, including biasing and AC operation. Frequency independent and frequency dependent SPICE modeling. MU-A741 DC and AC analysis, bipolar. MU-A741 frequency response analysis, including gain and phase margin. CA3140 DC and AC analysis, BIMOS. Characteristics of comparators and LM111 circuit description, bipolar, definition of a precision operation amplifier and a wideband or video operational amplifier, trends in operational amplifier performance. Summary. A general operational amplifier consists of an input section, usually a differential amplifier with either a passive or active load, an intermediate section, usually a single-ended common emitter amplifier with either a passive or active load, and an output section, usually a Class B or AB amplifier. This system concept was demonstrated by designing a simple 5-transistor operational amplifier using a CA3096 NPN/PNP transistor array with results verified using a SPICE simulation. A systematic application of a qualitative device function analysis, DC circuit analysis, and AC circuit analysis was then applied to the MU A741 operational amplifier. The MU A741, although one of the earliest commercially available operational amplifiers, is still used as a reference for the design and operation of many newer IC amplifiers. Using an approximate approach to avoid unnecessary algebraic complexity, we obtain values for internal DC currents and the resultant AC values of small signal voltage gain, differential input resistance, and small signal output resistance. These computed values were compared to the manufacturer's datasheet and a SPICE simulation. A similar but less detailed analysis was applied to a CA3140 operational amplifier. The CA3140 was selected because it represents the integration of MOS and bipolar technology on the same die. Key differences, especially the considerably higher input resistance, were noted between the CA3140 and the MU A741. Many electronic systems require the conversion of an analog signal to a digital signal and vice versa. A comparator can be used for this analog signal to binary output conversion. We will explore this concept and implementation in more depth in Chapter 16. As an extension of our analysis of typical operational amplifiers, the qualitative circuit description of the LM111 comparator was presented. Additional circuit complexity is the result of incorporating strobe operation and an increase in switching speed. The circuit analysis approach used to analyze the CA3096 transistor array operational amplifier design was, as well as the MU A741, CA3140, and LM111, serve as a foundation for understanding a wide variety of analog ICs. In addition, we observed by examining different IC specifications that there have been considerable improvements in DC performance, bandwidth, and power handling capability. Survey questions, problems, references. All right. Part 3, digital circuits. Having studied the operation and modeling of BJTs and FETs in chapters 4 and 5, we are prepared to look in depth at typical switching circuits. In switching circuits, these active devices operate in discrete states like on and off, rather than in the active region as linear circuits do. The reader should have a basic understanding of logic functions, and our emphasis will be on the devices. Digital logic circuits are exclusively in the domain of integrated circuits. Our approach to these topics will be to progress from the elemental building blocks of digital circuits, gates, to larger functional circuits, to subsystems, to systems. It is helpful to classify digital ICs by degree of integration, such as small-scale integration, medium-scale integration, large-scale integration, very large-scale integration, and ultra-large-scale integration. Okay. In Chapter 13, we focus on the circuits and operation of gates, which will provide familiarization with concepts that are common to all digital circuits and allow us to readily compare the various implementations of these gates. Digital ICs are realized with both FETs and BJTs in several different technologies. Each of these approaches has certain advantages in speed, power consumption, circuit density on the die, versatility in interconnection, and cost or ease of manufacture. Most of these concepts are best understood at the gate level. Commercially available SSI examples of gate level logic are compared, CMOS, TTL, and ECL, as well as some technologies not available in SSI, NMOS, BiCMOS, MESFET, and IIL. In Chapter 14, a number of examples of digital logic functions that have been implemented in SSI and MSI are examined. These are basic building blocks for all digital circuits and include both combinational logic, encoders, decoders, multiplexers, demultiplexers, arithmetic units, etc., and sequential logic, flip-flops, shift registers, counters, etc. Designers of systems where the production volume does not warrant custom IC design would incorporate these functions into a system design by interconnecting MSI packages on a printed circuit board. Designers of systems of reasonable production volume would incorporate pre-designed functional blocks into application-specific integrated circuits, or ASICs. Memories are outstanding examples of VLSI circuits. This came about for two reasons. First, memories are large and well-ordered arrays of devices, which made them easy to arrange into a very dense IC. There can be up to several million cells. Second, an intense design effort was justified because of the great potential production volume. In Chapter 15, we consider the ICs that have evolved from this application. NMOS and CMOS are the dominant technologies here, and for programming by the user, there are two NMOS devices called FAMOS and FLOTOX. Random access, read-only, and charge-coupled memories are discussed. Because the same technology is used, we consider programmable logic arrays, PLAs and PALs here. Analog to digital and digital to analog converter ICs and systems are the subjects of Chapter 16. These provide examples of the interconnection and or integration of the functional blocks discussed previously into subsystems that have wide application. Various system approaches to AD conversion are evaluated. Chapter 17 provides additional examples of IC system applications, each an important topic in its own right. Included are switch mode power supplies and regulators, 4-quadrant multipliers, and phase lock loop circuits. Part 3 may be undertaken immediately following Part 1 because it is independent of Part 2. Chapter 13, Integrated Circuit Logic Gates. Digital operation of circuits, basic gate terminology, early integrated circuit logic families, transistor logic, emitter coupled logic, NMOS logic, complementary MOS logic, integrated injection logic, comparison of logic families. Digital or binary systems ranging from very complex computers down to elementary switching circuits are made up of simple logic building blocks called gates. These logic circuits provide both the simplest and most widespread transistor applications. At the same time, logic gates lead very naturally to the fabrication of many transistors on the same silicon chip or integrated circuits. This chapter assumes that the reader is familiar with the NAND and NOR functions of a binary variable, reviewed in Appendix C. If you have had no prior exposure to the subject of digital logic theory, you can benefit from some additional reading. We now proceed to analyze circuit realizations of representative gates with the goal of familiarizing the student with fundamental digital electronic circuits. Short discussions of how the now obsolete resistor transistor logic RTL and diode transistor logic DTL are included to show the evolution of IC logic families. RTL is also a good pedagogical vehicle to define basic gate and transfer characteristic terminology. A logic family is a set of similarly configured logic circuits that can be interconnected according to simple rules without fear that driving gate output voltages are inappropriate for driven gate inputs. Although analysis of the internal circuit details is not necessary to enable the logic designer to use integrated logic packages in a system design, it does provide great insight into some of the design trade-offs made by the IC designer. Many engineers work at the device and gate levels of design in addition to the system level. The dominant logic families, as of this writing, transistor logic, emitter-coupled logic, and complementary MOS logic, CMOS, are treated in some depth in this chapter. Other digital technologies not associated with SSI families, such as NMOS, BiCMOS, and GA gallium arsenide MESFETs, are also discussed. As an optional topic, integrated injection logic, IIL or I2L, is also discussed. Because many of the concepts, such as merged transistors and current mode switching, are very much involved in present-day circuit development. In new systems, dominance is passing from TTL to CMOS, and IC design is moving from interconnecting SSI and MSI families to application-specific integrated circuits. We will refer to ASIC design in chapters 14 and 15. Important concepts in this chapter. Noise margin is a measure of the ability of a logic family to perform properly in the presence of temperature and supply voltage variations and other noise. Fan out is the number of inputs that a given gate is capable of driving properly. BJT saturating logic like RTL, DTL, and standard TTL experiences delays due to storage time in saturated devices. TTL logic using Schottky BJTs avoids the storage time delay of standard TTL. Tri-state output circuits allow buses to be driven without conflict. ECL uses a current switching arrangement to avoid saturation of the BJTs. Sub-nanosecond rise times require careful circuit layout and line terminations. MOS logic offers circuit density and fabrication cost advantages over BJT logic. NMOS logic with enhancement mode drivers and depletion mode drivers constitute a compact technology viable for VLSI such as memories. Both power dissipation and delay time in MOS circuits are proportional to CT. Gallium arsenide MESFETs gates are extremely fast because of the high mobility of electrons in gallium arsenide, and the saturated velocity is higher. CMOS offers reduced time over NMOS and negligible standby power. Power dissipation in CMOS is proportional to switching rate. CMOS combines the low power, compact, and fast CMOS gate with the current capacity of the BJT output stage. IIL is a very compact technology, but is at a disadvantage because its logic levels are incompatible with other digital technologies. Noise margins are a measure of how immune a logic gate is to unpredictable circuit disturbances, such as transients on the power lines. Note that noise margins will vary with fan out. Note a 30 milliamp pulse with a rise time of about 1 nanosecond would create a large voltage spike even if the power supply inductance were very small. Bypass capacitors alleviate this problem. Summary. A wide variety of digital technology is available to the logic designer. The basic binary variable functions not, and, or, NAND, and NOR are common to all digital design. Combinational logic is given a cursory review in Appendix C. We assume that most readers of this text will study digital logic theory in more depth in other courses. Our approach to this subject has been first to consider gates as building blocks in their own right, and then, in later chapters, to consider larger scale design. Thus, we have given an emphasis here to those technologies for which a logic family exists, even though modern design is moving toward a more integrated approach. These logic families are divided according to IC fabrication technology and basic logic gate configuration. In most cases, fan-out for all of these technologies is limited by speed considerations rather than DC loading. TTL is a very important BJT logic family because of its widespread maturity and application, and our emphasis on basic IC internal circuit realizations provides a good understanding of the terminal characteristics. The evolution of circuit variation gives added meaning to the general terms noise margin, propagation delay, and fan-out. New design is moving away from TTL in favor of CMOS. Among the other BJT logic families, ECL is very fast because of its non-saturating logic, but at the cost of relatively high power dissipation with its attendant problems. There is also the factor of power supply and logic level incompatibility with the other major technologies, so that its major use is in system-wide design where speed is the overriding consideration. Digital to analog conversion is another example. CMOS is the technology of choice where very low standby power consumption is desired. This is a rapidly maturing technology with a large variety of circuit functions in the families, which makes it very versatile in new design. The low cost and lower power supply requirements are making this the dominant technology as of this writing, where new design is moving towards application-specific ICs. For very large-scale integration, it is preferred over TTL because of low power, and where there is no external capacitive load, it is just as fast. To interface with capacitive loads, BiCMOS can be used. NMOS logic is very widely used because of its relatively simple fabrication technology and high circuit density. In general, NMOS logic is slower than BJT logic, and the former requires less power. NMOS has its greatest application in VLSI circuits where its circuit density is exploited, such as IC memories and microprocessors, but even there it is losing ground to CMOS. It is not used in small-scale integration. Gallium arsenide MESFET technology promises extreme speeds at low voltage, but at present the expense of fabrication limits its use to the special cases that demand that level of performance. BiCMOS offers the best of both bipolar and CMOS technologies at increased cost because of the more complex fabrication involved. The very compact structure of IIL illustrates its advantages in large-scale integration, but its incompatibility with the logic levels of other logic families limits its application to special-purpose circuits. It has the attractive feature of allowing the user to make the final trade-off of speed versus power in each application. Chapter 14 provides a more systems-oriented approach to the design of more complex logic functions using basic building blocks made up of combinations of gates, discussed in this chapter. Chapter 15 considers memory circuits as very large-scale integration of these gates. Chapter 14, Small Digital Subsystems. Combinational logic circuits, sequential logic circuits, monostable and astable timing circuits, data system examples. The manufacturers of logic families, CMOS, TTL, ECL, combine logic gates into arrays that accomplish specific functions. As previously noted, medium-scale integration, MSI, implies about 12 to 100 gates on a chip. A representative listing of such circuits is presented in Table 14.1. With CMOS, the variety is greater than with the bipolar families. This chapter identifies some typical logic families that are frequently used in logic design, and it is convenient to take examples that have been implemented in MSI circuits in the past. This is a representative list of MSI functions implemented in the logic families. It says MSI die may have multiple independent circuits on one chip. Depending on the number of pins in the package. Where appropriate, outputs are tri-state. No attempt has been made to be exhaustive. Most of these functions are also identifiable as portions of VLSI and ASIC designs. All right, this is a list of applications. Schmidt triggers, 1 or 2 inputs. BCD to decimal decoder, BCD to 7-segment decoder, active high, active low, D flip-flop, JK flip-flop, 4-bit full adder, 4-bit magnitude comparator, decade counters up or down, decade up-down counters with parallel load, divide by 12 counter, 4-bit binary counters, 4-bit binary up-down counters, 8-bit counters, frequency dividers, 4-bit shift registers, 4-bit bidirectional shift registers, 8-bit shift registers, monostable, with or without clear, retriggerable monostable, 2-bit 4-line decoder / demarks, 3-bit 8-line decoder demarks, 4-bit 16-line decoder demarks, 4-input multiplexer, 8-input multiplexer, 16-input multiplexer, 8-line priority encoder, 4x4 register file, 4-bit arithmetic logic unit, look-ahead carry generator, octal bus line drivers, octal bidirectional line drivers, 8-bit addressable latch, 4x4 binary multiplier, quad or octal transparent latch, 9-bit parity generator checker, 64-bit RAM, voltage controlled oscillator, frequency dividers, and rate multipliers. Having defined the functions and characteristics of several examples of these circuits, you will be able to appreciate how the circuit designer can combine these standard building blocks into larger arrays, logic systems, or subsystems. Larger arrays can be in the form of MSI chips interconnected by copper traces on a printed circuit board, or they may be fabricated into large-scale integrated circuits, LSI, having 100 to 1000 gates per chip, or even very large-scale integrated circuits, VLSI, of 1000 to 10,000 or more gates per chip. Recent ULSI, ultra-large scale integrated circuits, are on the order of 1 million gates per chip. When the IC designer integrates many of these functions specific to one application into one die, it becomes an application-specific integrated circuit. This is justified when the specific industrial demand allows amortization of the additional design cost. Gate arrays are also available, for which only the metallization layer steps need to be modified to provide custom interconnection. In general, MSI logic families are decreasing in importance, being replaced by VLSI gate arrays or ASICs. One class of logic functions is called combinational logic, meaning that the outputs are dependent only on the present inputs. As examples, we consider multiplexers and demultiplexers, decoders and encoders, and a simple arithmetic logic unit. Another class of logic operation is referred to as sequential logic. This means that the output depends not only on the present inputs, but also on the past history of those inputs. Examples include flip-flops, registers, and counters. We present the concept of synchronous and asynchronous timing. No matter how complex an IC may be, the basic building blocks we are going to discuss are the same, of course, replicated many times and appropriately interconnected. Design examples are used to illustrate the application of these logical building blocks into small systems. The subject of transmission line drivers and receivers is discussed in the context of practical transmission between circuits. Although many designers associate the term ASIC with digital applications, ASICs are available for analog as well as mixed signal applications. Important concepts in this chapter. The outputs of combinational logic circuits depend only on the present inputs. Digital multiplexing allows conversion of parallel data to serial data and permits several circuits to communicate on one channel. A decoder allows an n-bit code word or an address to choose one of 2 to the power of n locations and can translate an n-bit code word into one of 2 to the n functions. The active input of an encoder generates the address of that input. An arithmetic logic unit has an output that may be any one of a number of functions of two input variables under the direction of a control word. The outputs of sequential logic circuits depend not only on the values of present inputs, but also on the past values of those inputs. An edge-triggered latch is called a flip-flop. These may also have direct set and reset. The edge-triggered flip-flop avoids race conditions and the ones catching problem. A register in an array of flip-flops. This array can be arranged to shift data between stages in the register. A counter is any array of flip-flops that sequences through its states when clocked. A monostable multivibrator is a regenerative circuit with one stable state and one quasi-stable state. It is used to create a pulse of predetermined width. An astable multivibrator is a regenerative circuit that alternates continuously between its quasi-stable states. It provides a free-running digital waveform. Line drivers and receivers match data signals to long transmission lines. A function table or truth table for a combinational logic function lists the possible outputs for every combination of input. Summary. The basic logic circuits presented in Chapter 13 are organized into a wide variety of combinational and sequential logic functions. These logic families are available in a number of technologies such as TTL, CMOS, and ECL. Here we discuss several key building blocks common to logic systems from a functional viewpoint, independent of the fabrication technology. Today's circuit designer may never use these functional blocks in the form of MSI ICs. Rather, these blocks may be implemented in a VLSI ASIC, either by custom interconnection of an array of logic modules at the top metallization layer, or by programming the interconnection in some type of field programmable logic device. We pursue these options further in Chapter 15. We presented circuit symbols, function tables, and logic diagrams for multiplexers, demultiplexers, decoders, encoders, arithmetic logic units, latches of various types, registers, and counters. To explain the operation of these logic building blocks, we use timing diagrams as well as typical design applications in small systems. Timing circuits, including monostable and astable multivibrators, were considered. Monostable multivibrators are used for generating pulses in digital circuits, and astable multivibrators serve to provide clocks for driving digital systems. A very few centimeters of separation between logic circuits may be significant, with rise and fall times on the order of 1 nanosecond. However, proper termination can eliminate reflections, and well-designed transmission lines can minimize noise pickup. When data signals must flow between logic circuits separated by significant distance, transmission lines with line drivers and line receivers are required. We discuss systems using balanced lines with twisted pairs of conductors, coaxial cables, and fiber optic channels. Chapter 15. Semiconductor memories. Overview of semiconductor memories. Introduction to memory organization. Read-only memories. Static read-write random access memories. Dynamic random access memory. Charge-coupled devices. Gate arrays and programmable logic. Summary. A means of storing information is essential to any computing system. Information can be numbers to be manipulated, the names of customers, program instructions to tell the central processing unit what to do, or a myriad of other types of data. Such data can be stored permanently outside the computer on magnetic media such as diskettes or disks, tapes, or bubble memories. Compact disks, read optically, have extremely dense data storage capabilities. The relative permanence of such storage is offset by the long access time. Semiconductors are predominantly used for the high-speed memory inside the computer. Semiconductor memories are presented in this chapter not only because of their great importance in processing systems, but also as the principal application of large-scale integration, more than 100 gates per chip, and very large-scale integration, more than 1,000 gates per chip, or 10,000 transistors per chip, and ultra-large-scale integration with millions of transistors per chip. Thus, semiconductor memories are on the frontier of fabrication technology. Indeed, a semiconductor memory technology has become so diverse that we will refer to the tree shown in figure 15.1 just to categorize the major applications. In nearly every case, the technology will be MOS. Because of their similarity to read-only memories, ROMs, programmable logic arrays, PLAs, and programmable array logic, PAL, are discussed here also. Finally, we survey the development of field programmable gate arrays, FPGAs. Each of these devices allow the user to achieve ASICs in the field at reasonable cost because the many users result in high volume to the fabricator. Important concepts in this chapter. Random access memories include read-write and read-only. Dynamic read-write RAMs are very compact and low cost, but also very volatile. Static read-write RAMs are fast and are not volatile as long as DC power is maintained, but cost more and use more power than dynamic memories. Field programmable ROMs are either permanently programmed or erasable. Erasable ROMs are either erased by UV radiation or are electrically alterable. Flotox memory cells are programmed and altered by Fowler-Nordheim tunneling. Non-volatile RAM combines a static RAM with an EEPROM. Static read-write memory requires up to 6 transistors per cell. Dynamic read-write memory consists of 1 transistor and a capacitor for each cell. Pseudostatic or integrated RAM has refresh circuitry on the memory chip. Charge-coupled devices store data as charge packets on the surface of a silicon substrate, separated from a positive plate by a thin oxide layer. Gate arrays combine economies of scale with custom interconnections. PLAs and PAL are large-scale integrated circuits where certain interconnections are field programmable. That's an interesting thing if you want to have a look at that. That's the tree of semiconductor memory technology. Nearly missed the summary there. Large semiconductor memories are relatively inexpensive because VLSI technology has made great advances in compacting more bits per chip. This has come about because the great demand for larger memories has fueled much research and development, and because the structure of the memory is amenable to scaling and expanding. Table 15.1 compares representative commercial memory chips. An attempt was made to compare similar speeds and technologies and to use current prices in tens quantity. Power is dependent on clock rate. The other chief applications of VLSI technology are also in high production volume, rather structured ICs like microprocessors and logic arrays. We have avoided much discussion of microprocessors, considering them a subject in their own right. ASIC custom gate arrays are very important in designs where the volume warrants the development costs and time. A very attractive alternative for prototypes, for low production volumes, or for quick development time is one of the various programmable logic devices. CMOS PALs, controlled by an internal EEPROM switch matrix, seem appropriate for logic systems under 1000 gates, while larger systems should consider FPGAs with CMOS EEPROM technology. Table 15.2 summarizes some of the important considerations. Chapter 16, Analog to Digital and Digital to Analog Conversion. Analog to digital conversion process, digital to analog converters, analog to digital conversion, summary. To this point in the text, we have categorized electrical signals as analog, continuous, or digital, discrete. An analog signal is defined as a continuous function in time with a continuous first derivative. Fundamentally, all variables such as voltage, current, pressure, temperature, velocity, etc. are analog signals. This is because physical processes tend to oppose discontinuities in these variables by preventing infinite rates of change. To use a digital computer or microcomputer for computation and subsequent signal processing, these analog signals are coded as a binary digital signal by means of an analog to digital converter. This approach is used in remote control telemetry application and for communication system signal processing. Other applications include digital instruments such as digital voltmeters and computer networked instrumentation. A complete analog to digital converter, an ADC system, that could be used as an interface for a computer controller is shown in figure 16.1. Typically, a single ADC circuit is used to process a number of analog channels, VIT, where I equals 0, 1, 2, M, where M is usually designed to accommodate multiples of 8 input channels. The sampling order and interval is under computer control logic to obtain the digitized value of each of the analog inputs at some given time. A sample and hold circuit using a circuit with some type of capacitive storage element is used to obtain an instantaneous time invariant value of one of the analog inputs when it is being sampled. This voltage sample taken at time Ts, VSTS, is then input to the ADC for digitizing. The binary digitized signal is then stored or buffered in a parallel latch until it is needed. The resultant n-bit digital output word relates as a binary fraction to the full-scale reference voltage. Okay. Bit Dn is called the least significant bit because it represents the smallest weighting, and D1 is called the most significant bit because it represents the largest weighting. A representative transfer characteristic for a 3-bit ADC is given in figure 16.2. The resolution is 1 LSB and is given by delta V equals VFS2 to the power minus n. The resulting quantizing error or error voltage is defined as the difference between the ideal transfer characteristic and the digitized equivalent. This error voltage, which lies between plus or minus 1/2 delta V, is plotted in figure 16.2b. Note that this characteristic has rounded the input analog value to the nearest digital code value, which minimizes the error. There are 2 to the power of n binary code values. We discuss a number of types of ADCs in section 16.3. Consider the AD example of the process of reading a thermometer. One usually looks at a volume of liquid as in a glass tube, assumes that the level is proportional to the temperature, and then expresses the temperature by rounding off this level to the nearest discrete code on a conveniently calibrated scale. Consider a Fahrenheit thermometer calibrated from minus 17 to 110 degrees in the decimal code. It would take 7-bit code words to cover this range in binary. On the other hand, having manipulated these variables in digital form, it is often necessary to convert them back to analog signals, digital to analog, in order for them to be compatible with physical machines, transducers, etc. We shall examine both of these interfaces between analog and digital signals and circuits in this chapter. Important concept in this chapter: analog to digital conversion includes sampling, quantizing, and coding, the sampling theorem and sample and hold circuits, quantization, resolution and noise, binary weighted resistor DACs and ladder DACs, bipolar and CMOS examples of DAC, parallel or flash ADCs and cascaded flash ADCs, successive approximation ADCs, single slope and dual slope ADCs, counting or tracking converters, switched capacitor ADCs, comparisons of ADCs, speed and complexity. Summary. It is becoming more and more common to convert analog signals to digital form for processing or communications and then convert them back to analog. In communication systems, it is a common method for multiplexing many signals into a common channel called time division multiplexing. It is also a common method for communication systems to trade bandwidth for signal-to-noise ratio. There are countless other applications. The process of converting a time-varying analog signal to a digital signal involves sampling frequently enough to specify the signal completely and then quantizing each sample into a digital code word. If the analog signal is band limited with a bandwidth B, it has been determined that the signal can be represented by at least 2 B samples per second without any loss of information. When the analog signal varies appreciably during the conversion time, it is necessary to use the sample and hold circuit. We have seen how the maximum error in the quantizing process is affected by the number of bits in the sample code word. The need to work with both analog and digital techniques is even more explicit when studying AD and DA converters. Current fabrication technology permits the combination of many of these functions on the same die. This is especially true with CMOS, where each of the various ADC and DAC schemes that we have discussed has been integrated into self-contained converter systems or into ASIC systems. Using the basic IC building blocks and techniques, we discussed a variety of ADC and DAC circuits. Table 16.1 summarizes the key features of several DACs. Okay. One ADC technology that is especially suited to CMOS circuits is the charge redistribution method of successive approximation. This scheme uses binary weighted capacitors rather than resistors in the internal DACs ladder. Another recent innovation is bi-CMOS converters, where the best features fast bipolar switches and low power CMOS logic can be combined. Chapter 17. Additional examples of analog integrated circuits. Analog systems overview, series pass voltage regulator, switching regulators, analog multipliers, phase locked loop system and circuit description, phase locked loop applications. So far, we have focused on the internal circuitry and function of operational amplifiers, as well as their overall system operation utilizing feedback. A large variety of analog integrated circuits whose function is not explicitly amplification can be studied using techniques developed in the preceding chapters. Section 17.1 presents an overview of analog IC systems with a focus on the burgeoning use of ASICs for embedded applications. Indeed, most electronic systems employ a mix of analog functions, digital microprocessors, and digital glue logic and control logic. In addition, we observe that all electronic systems require compact, regulated, efficient power supplies. Many systems are required to communicate with other systems via digital-based protocol networks using copper, optical, or radio frequency links. Contemporary electronic circuit design mirrors these needs by recognizing the wide variety of digital and analog functions required. This chapter, along with chapter 16, AD and DA material, presents a brief discussion of some more widely used functions. In section 17.2, we introduce the series pass voltage regulator as an example of an integrated circuit that utilizes amplification and negative feedback to obtain a function other than amplification. Similarly, in section 17.3, we present examples of switch mode power supplies to illustrate the operation of negative feedback to control the pulse duration rather than the amplitude. After all electronic systems require some type of DC power. In section 17.4, we examine analog circuit techniques that are used in the multiplication of signals to obtain modulation, demodulation, mixing, and phase detection functions. These are very important for communications systems-based functions. Phase detection and negative feedback are combined in the phase locked loop, whose system and circuit descriptions are presented in section 17.5, along with selected applications in section 17.6. Again, many of the applications are based on data link communication needs. Important concepts in this chapter: definition of voltage regulation and a block diagram of a voltage regulator, voltage series feedback applied to a series pass voltage regulator, qualitative operational description of a switch mode voltage regulator, comparison between series pass and switch mode voltage regulators, 3 regions of operation of a Gilbert cell multiplier, system applications for multipliers including modular, demodular, phase detector, and phase lock loop, block diagram and qualitative operational description of a phase lock loop, properties of zero and first order phase lock loops, definition of a lock range and capture range, application of a phase lock loop for FMD modulation and for frequency synthesis. One can buy almost complete AM and FM radios on a chip, as well as major television subsystems. Often a company will design and implement an ASIC that contains proprietary circuits and systems and are often labeled with a special custom part number. There are literally tens of thousands of functions of varying complexity available as an off-the-shelf IC or configured from ASIC digital and analog arrays. A mathematical treatment offered in communication system textbooks would show that the frequency translation is the result of the convolution of 2 impulse functions. Summary. Using basic IC building blocks and techniques, we discussed a variety of primarily analog circuit functions, including series and switching power supply regulators, multipliers, and phase-locked loops. Voltage-regulated design requires combining basic amplifier, power amplifier, and both negative and positive feedback concepts. In addition, packaging and heat dissipation are important issues for this application. Multipliers as circuit elements or as subsystem phase detectors in a phase-locked loop depend quite strongly on the matched device fabrication inherent in IC technology. When included as part of a PLL, negative feedback for the entire loop and positive feedback for the VCO are important. Frequency synthesis techniques illustrate the need to understand both the analog and digital aspects of any electronic system. Fabrication technology permits combining many of these functions on the same die. Part 4, Semiconductor Technology. This section of this text includes only one chapter, but it is a very important chapter in that it provides an overview of the IC technology fabrication justification for the specifications of all the active and passive devices used in the preceding 17 chapters. Chapter 18 is written as a standalone chapter. Therefore, you could use this chapter either as a reference for this book or include it directly as part of the course. It would fit well right after Chapter 5, since by then you will have been introduced to all key devices. It is also useful to review the definitions and topics in Chapter 2 before proceeding to the study of Chapter 18. Chapter 18 only presents an overview and doesn't even come close to a comprehensive presentation. Consequently, you should avail yourself of opportunities to take complete courses, perhaps with a laboratory, in semiconductor device fabrication and semiconductor device physics. As you continue your studies in electronic circuits and systems, whether digital or analog, it will become increasingly important to understand the basics of device fabrication so that one can effectively compare the large and increasing number of technologies available to the designer. Therefore, Chapter 18 discusses the fabrication technology and resultant specifications obtained for resistors, capacitors, diodes, BJTs, JFETs, and MOSFETs. One should observe that SPICE models for all of these elements are directly keyed to fabrication parameters and geometries. Chapter 18, Basic Fabrication Technology and Device Constraints. Impurity diffusion, ion implantation, resistive properties of doped layers, photolithography and masking, resistors, capacitors, NPN transistors, PNP transistors, diodes, junction field effect transistors, metal oxide semiconductor transistors. Summary. Integrated circuit technology presents the designer and user of integrated circuits with many choices with respect to performance and functionality. Tens or even hundreds of thousands of individual transistors are fabricated on a single die using a variety of technologies, and each addressing different applications. Therefore, it is quite important that a designer become familiar with the various factors and technologies associated with the fabrication of ICs. The objectives of this chapter are twofold. The first is to provide an overview and reference of the various technologies used for IC manufacture so that the designer and the end user can understand the constraints of each technology. The second objective is to provide a foundation for advanced study. The term monolithic is derived from the ancient Greek mono, meaning single or one, and lithos, meaning stone. A monolithic circuit is an entire circuit fabricated within a single piece of suitably doped crystalline semiconductor, usually silicon. Figure 18.1 shows the progression of silicon ingot sizes from 19 mm used in the 60s to the very common 100 mm ingot used in the 80s, and currently a 200 mm ingot is now being used by some of the large manufacturers with 300 millimeter sizes in the near horizon. These ingots are nominally single crystal doped silicon, usually grown by the Chuzralski process. This process is diagrammed in 18.2. Basically, the crystal is grown by immersing a seed crystal in molten silicon, suitably doped, and then cooling it gradually to less than 1412 degrees Celsius as the crystal is pulled from the melt. Again, we will mention certain applications in gallium arsenide and other 3 to 5 compounds only in passing, because for the most part such circuits are beyond the scope of this book. No integrated circuits are being fabricated in germanium, although the use of germanium emitters in high frequency bipolar technology is being explored. We first consider the fundamental steps in planar technology, in which all components are fabricated on a single surface of a semiconductor. These processes are oxidization, solid-state diffusion of dopants, ion implantation, photolithography, the growth of epitaxial layers, and general material deposition. Early pioneers in these basic processes were Jack Street, Claire Kilby at Texas Instrument, Jack St. Clair Kilby at Texas Instrument, who in 1958 to 1959 demonstrated an RC oscillator and flip-flop. Robert N. Noyce at Fairchild Semiconductor, who in 1959 and 1961 proceeded to develop the foundation for the commercial manufacture of a logic family. In addition to the basics of solid-state diffusion, we will discuss ion implantation of impurities and the use of very short wavelength lithographic techniques. As a fundamental introduction to semiconductor device processing, we have elected to provide a basic overview of key steps using fundamental analytical equations. An engineer working in the semiconductor device processing industry would use some variation of the semiconductor process modeling program, SUPREM. However, the use of Supreme is beyond the scope of this text. It is important to realize that the material and processing property graphs presented in this chapter are only approximations. Variations on the values and functional behavior of many of these parameters are often presented in the literature, and most semiconductor manufacturing facilities spend considerable time and money on generating precise test data to obtain reproducible results. With this basic caveat, we will illustrate how the basic steps are employed in the fabrication of passive components such as resistors and capacitors, and active components such as diodes, bipolar transistors, and FETs of various types. Important concepts in this chapter: qualitative description of semiconductor impurity diffusion, use of one-dimensional diffusion equation, infinite constant and finite source diffusion equation solutions and application to the formation of doping profiles, technique for growing of epitaxial layers, use of ion implantation, definition and computation of a dose, resistive properties of dope layers, definition and computation of sheet resistance for uniform and non-uniform layers, growth of SiO2 and applications of SiO2 in semiconductor device fabrication, basic steps in the photolithography or masking process, fabrication and properties of diffused and pinch resistors, fabrication and properties of MOS and junction capacitors, fabrication and properties of NPN transistors and of lateral and substrate PNP transistors, fabrication and properties of JFETs, fabrication and properties of MOSFETs, including CMOS, VMOS, DMOS, and SOI devices and circuits. Summary. Each integrated circuit fabrication technology offers both constraints and advantages for the designer and end user of electronic circuits. This chapter provided an overview of some of the major fabrication technologies as well as their applications. Although detailed semiconductor device processing information is beyond the scope of this text, we reviewed the fundamentals of impurity diffusion, ion implantation, and photolithography as they relate to the manufacture of both passive and active components. Passive components include both diffused and pinch resistors and junction and MOS capacitors. A series of cross-sectional sketches illustrates the fabrication of the NPN transistor. Many of the other passive and active devices are manufactured by means of the NPN transistor fundamental process, but with different circuit functions defined by different photolithographic masking and metallization processes. Similarly, we also presented descriptions and cross-sectional sketches of several different MOSFET families, with NMOS and CMOS being of the most current interest. All right, now we've got Appendix A, a list of symbols. All right. Looks like we missed an appendix there. Appendix B, physical constants and conversion factors. Appendix C, number systems and Boolean algebra. Appendix D, introduction to SPICE. Appendix E, two-port model summary. And Appendix F, answer to selected problems. There's the answers to the problems. And then the index begins. And that's everything, I think. Was there something on the... Oh, there was something at the back that we were going to look at. What was that? That was the... Get the professional design edge with Electronics Workbench. The student edition of Electronics Workbench lets you interact with circuit simulations in real time, allowing you to develop the intuitive feel for circuit design you get from working with actual components. There you go. And is this, you can write in with your credit card number. They're selling the student edition of Electronics Workbench at $59.95, and Electronics Analysis and Design using Electronics Workbench, a bookware companion lab book, $15. And I would like to purchase, you can get both of them. And hopefully I'll get the CD-ROM at some point in the future. And if I do, I'll include the link in the show notes. But that's it. We made it to the end. So I'll throw you over to the farewell can and we'll wrap up. That's a wrap. So yeah, that was our old book teardown of Principles of Electronic Circuits, second edition. I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.